heat just to heat up the water and cooling it down. I'm not saying this technology or liquid solvent is not a bad thing. So we should focus on how to improve that heat exchange and how to make it heat transfer efficient for sure. And we are doing that by doing large scale demonstration. But at the same time, wouldn't it be nice if we have amine functional groups still really effective at capturing CO2, but maybe get rid of all the water weight in the system? So second generation CO2 capture liquid solvent, I'm not talking about solid solvent here. Liquid solvent was waterless, or you call it water lean, anhydrous, or waterless CO2 capture liquid solvents. So these were second generation, I believe, about decades long of research we've been doing. Some of you may be familiar with ionic liquid, right? Ionic liquid without water is salt, right? A cation and anion. So there are many of my colleagues, including John Bernicki, worked really hard in those materials. So when I started about a decade ago in this research area, I looked at ionic liquid, and it was way too much organic chemistry. So for me, I'm more picky person. So I said, well, is there a material similar to ionic liquid, which has great mix of many combination of ionic liquid you can make, and chemical physical tunability is amazing. So I was looking for something similar with the great properties. And that's when Lyndon Archer at Cornell University called me and said, Alyssa, I made a really unique material behave similarly to ionic liquid. Has almost zero vapor pressure. There are so many combinations of these materials we can make. Can we do something about CO2? And that's our story started. So if you look at this material, we start with a suspended nanoparticle, less than 20 nanometer in general. And we can tether polymers either covalently or ionically. And final product, most important thing is after get rid of all the water, you end up with this liquid-like material. So it's like a self-suspended nanoparticle, but they don't agglomerate. It's liquid-like behavior. So first thing was, if you start with the liquid polymer, which is short brush like this, like less than 2,000 molecular weight, it's very tiny, its thermal stability is not very high. So what we really wanted to see was, by grafting these polymer onto nanoparticle, can we this is our 2D ROSY NMR data showing that after we made all these, left-hand side and right-hand side is the left-hand side is the polymer we started with. On the right-hand side is the same polymer now tethered onto the nanoparticle. And if you're not familiar with it, was that from untethered polymer here, we really increase the window of opportunity for thermal stability by tethering those polymers onto nanoparticle. But this is just one scan, a TGA scan. But what is more important is, can we use these materials in thousands and thousands cycles to be economical? That's very, very critical for commercialization. So if you look at the right-hand side, we actually did up to 100 cycles. Gnomes last really stable. But then the polymer, which we started with, degrades almost 80%. So this has really good chemical property for CO2 capture, but we cannot deploy this in the industrial scale because it will be degraded way too fast. So that was really interesting. So we started looking into, well, now we know that it's a thermal stability, especially oxidative thermal stability is fantastic. We're going to use this. But now we have to just decorate all these polymer chains with the amine functional groups as much as possible. And as we expected, as we put more amine functional groups, your CO2 capture capacity goes up. This is expected. So this was really fantastic news. We got super excited, but then now we have to start thinking about, remember that huge reactor in the power plant? How are we going to put these synthesized and putting it in there? So we start making point. And then one of the next thing we looked at was viscosity. Because if you remember the photo, it kind of looks like punched. We need to figure this out. So we started thinking about this, and my friends in ionic liquid fields, they were like really brave. They said, oh, we can control the hydrogen bonding network and we can reduce the viscosity. And in fact, they did. So they were able to lower the viscosity quite a bit to the range you can pump it around, like maybe 40 to 60 centipoise. But I was looking at our material gnomes, which is like thousands and 10,000s. There's no way. I can try, but maybe it's not worth my time. But we start thinking that, well, challenge means another opportunity to think this upside down. So if I still like this liquid solvent, which is very unique, very oxidative thermal stability is fantastic, and tunability is great, but we just don't like high viscosity. So we thought that working with Lawrence Livermore National Lab, if we can chop them, this honey-like liquid, and package them, maybe we can avoid all these issues with high viscosity. So the first generation of this technology, working with the Lawrence Livermore National Lab, was let's design a microfluidic device. Of course, it's really hard to scale up, but it was really easy to make controlled encapsulated liquid solvents. So if you look here, this microfluidic device will have blue colored with the dye, our NOMS material inside. The white fluid is UV curable polymer. So now you're making droplet instead of droplet, right? Many of them. And then downstream, you just need to do UV cured. Now you will have a shell which is solid but gas permeable, and then liquid will be intact. But the good thing is, if I put this blue fluid, which is water, it will just evaporate over the time. But because our material has almost a near zero vapor pressure, it stays intact. So this is actual material we actually made. So you can make with a single core or multi-core. There are many different controlled. We can look at the different sizes of the overall micro beads, or inside what we're gonna put in, and different mixtures and all that so on. High tunability again. So it's interesting now, right? Because now you have a benefit of having liquid solvents and solid sorbent in one package. And as we expected, by doing so, we were able to create a lot of interfacial area, and then we were able to make the kinetic of CO2 capture much faster than we expected. Or we started with. And of course, this rate will be determined by how much of the gas-liquid interface we created, so that this one was a lot faster than single core, and depending on the size. So next generation we started thinking about was, maybe can we make it even go further, creating even more interfacial area? So instead of using microfluidic device, what we ended up doing was mixture of a shell material, UV curable shell material, and our highly viscous NOMS material into one, and we used a strong shear, high shear, to make immersified system. And then we spread these into flat surface, and then we had to UV cure, and now we have a materials like this. We call it SIPs, which is solvent impregnated polymer, and now have a very, very tiny droplet, which is less than micron size of all these droplets, well distributed in the system, or at least that's what we hope to make. And here are some of the data. So if you look here, you can go all the way from about 9% all the way to almost 50% loading of NOMS, and this is just a pure shear mixing of these materials. And you can kind of see some of the droplets at the lower concentration, but by the time 50%, it's almost like a well-mixed system. And if you UV cure them now, cure them into a solid system, it looks like a solid membrane, but there are a lot of liquid droplets inside. And here, this is SEM images, and we wanted to see whether our materials are well distributed. So we kind of follow the amine, so nitrogen group. So you can see that it's well distributed. And using this, we were able to really capture CO2 much faster way. Yes. Oh, there we go. So then now our reaction kinetic, CO2 capture kinetic was orders of magnitude improved. And now your reactor design, previous liquid solvent versus this material will be very different. So you can have fluidized bed reactors or duct injection. There are many different ways to apply this technology. Another interesting thing we did was, how many of you are working on MOFs in the audience? If so? Good, at least one. So I thought this is another interesting thing, because I'm not going to cover too much about our MOF work, metal organic framework, but one of the challenges with MOFs are that it doesn't like water, many of the MOFs, right? So I thought that if we can actually synthesize MOF directly inside the capsule, maybe it can be protected because it'll be hydrophobic surface. At the same time, we can kind of package the nanocrystals or sub 2 micron crystals of MOF inside. And we were actually able to do that. So this is HCOS MOF, and then we actually encapsulated MOF precursor solutions, and then we UV cured the shell And as you increase the temperature, you can see that the synthesis moth was a lot faster. So I think there are a lot of questions we can ask. What is the moth synthesis behavior in this confined capsule environment? But I'm not going to talk about that today. So let's talk about what now. Like, what should we do once we capture CO2? That's a big question, because we're not going to do catch and release, and it didn't do anything then to the environment. So one thing you really need to do if you care about climate change is we need to store. Because we have way too much CO2 to make good stuff, and you'll flood the market very quickly. And we really draw down so much carbon dioxide. I'm not going to talk about a lot on this, but at least I can tell you that there are enough storage tank underground in geological formations. Nature has all these pockets of areas we can actually inject CO2. And in fact, some of the places we can even carry out the reaction of one of the very few downhill reaction from carbon dioxide right here. So you can make like limestone, like artificial limestone, much faster. You're kind of pushing the earth to do the weathering of the rocks a lot faster. There was a lot of interesting data came out, especially Iceland. There's a Carfix project showing that after injecting CO2 or carbonated water, within 2 years, they were seeing that these crystals forming, which is you actually fixed CO2 and capture CO2 into solid carbonates. But let's talk about something else. What else can you do, right? In a sense that most of us visiting here today, UNAM, we're going to be talking about CO2 utilization or conversion to useful product. So this is the interesting report came out written by McKinsey 2020. I think they should have upgraded version, but this is 2020 data. I think is still quite relevant. It was their prediction on how much CO2 storage and CO2 utilization we're going to do, making useful product by 2030. 2030 is only 8 years left, or 7 years left. Oh my gosh, right? So if you look here, this is a light gray bubble. Is their expectation of how much carbon storage we're going to do? I'm really hoping they underestimated, right? Because bigger this bubble is, will fix the climate change more, for sure. But interestingly, they also had these black bubbles. And these size of black bubbles are kind of comparable to the storage one, and which was quite surprising to a lot of people. And there are many different reasons. We could have a technology advancements, but also maybe market-driven or policy-driven, these bubbles of market. What they're saying is by 2030, we'll be making fuels, construction materials, biochar, and plastics and chemicals, all these from captured CO2. Interesting, right? This is very ambitious, but their prediction. And if you look here, this is in New York City, and I think we can even put the Mexico City here, and I think there is something covering, but these are chemicals you go around. There are a lot of things we actually use. So let's look into this room. Like, for example, there are chairs, there are you guys, and there's the monitors and all that. We talked about decarbonization. Can we decarbonize this room? Yeah, right? Any material coming from here, we can capture carbon and store, so that by the time it comes here, this new chair, we can make it decarbonized. But can we 100% decarbonize? No, if I do 100% decarbonize, it'd be poof, none of us will be here, right? Because we're made out of carbon too, right? So maybe term is we do need to do decarbonization, very important. But we need to also do defossilization, which means we still need carbon, right? But can we make sure that that carbon will come from non-fossil resources? This is an extremely big challenge, and we really need to do a lot of source searching on that. So that's where we led a lot of discussion on a whole new circular carbon economy. So in this big bubble called new circular carbon economy, maybe for next 10, 20 years, the way we use chemicals and materials and product as a consumer maybe doesn't change as much. We will introduce new chemicals for sure, but it may not, this entire bubble outside how consumer product is produced and consumed may not change as much. But what if we have input of only renewable energy and renewable hydrogen into this bubble? And if we can get the waste carbon and capture and convert. And convert means there are many different pathways. It could be biological, thermochemical, electrochemical, or hybrid systems. But we have to really think about the fact that this is a huge commodity chemical market, that without thinking about tech to market, we're not going to make it. What does it mean, right? Like, what does it mean by this particular market is very important. And this is not going to be done without talking about economics and policy. I think that's why carbon management or a whole new circular carbon economy brings every expert onto the same table, which is really fantastic and difficult at the same time. So let's think about this a little bit. And one thing I'm not going to talk about today is this little hydrogen. And depending on the carbon intensity of this hydrogen, this overall circular carbon economy will change again. So there are many different colors of hydrogen now. You heard about green hydrogen, blue, there's like a pink, and I think the latest color I heard is orange. So there are so many. So you have to choose the right color, right, to make it. So let's think about it. Non-fossil carbon, where would you get it? And it has to be a huge amount because we're going to be replacing the entire commodity chemical market. So as an engineer, I want to be very simplistic. Let's simplify to gas, liquid, solid. So what is gas, which has carbon in it? Atmosphere. Liquid, the ocean. Solid will be rocks. So rocks are nice because they keep the carbon out of the atmosphere. So let's not tackle the solid one. Then we have only two options with air and ocean. So we can definitely have these air and ocean, direct ocean air capture, direct ocean capture, or you're kind of covered, but then there's a terrestrial and marine biomass. You can go through biological pathway as well. Either way, you will have carbon for you, which is non-fossil. But obviously, harvesting this non-fossil carbon is not an easy task. It will be very challenging. So let's talk about the direct air capture. A lot of us have been working on over the years. So capturing CO2 directly from air is one of the most challenging technology because the concentration of CO2 is only 400 ppm or now maybe 410 ppm, parts per million. Compared to point source capture, which we've been talking about, in the coal-fired power plant, you have CO2 concentration of 12 to 15, which is much higher. So now your driving force is little. Another thing is, because this is a low concentration, if you're trying to scrub out 100% or 95% of CO2 from this system, it would be almost impossible. So even target will be very different. So our target is usually, if you can scrub out about capture CO2 from air over 60%, this is already good enough. Because the lower the endpoint of the concentration, more expensive this technology will be. But capturing CO2 from air has other issues in addition to concentration challenge. For example, here, we need to have a very low pressure drop because the amount of the entire air we have to process compared to flue gas is huge. So compressing all that air is impossible almost, right? So you need to have low pressure, whatever you do, low pressure drop. Another thing, in air, we have a lot of oxygen and that's why we can live, but at the same time, everything degrades much faster when there's oxygen. And also there's the sunlight and all that stuff. So how to make sure that we have a robust material with the long-term stability under high oxygen concentration, and also today can be sunny, tomorrow can be rainy days. How do we deal with all these? Because your input will be always fluctuating and including the temperature, winter days versus summer days. So a lot of us started working into this. One of the things I started thinking of doing was, remember our NOMS material has almost zero vapor pressure? So if I have a cup of this sitting outside, it'll be happily just sitting there. It doesn't evaporate, it doesn't go anywhere, it doesn't degrade. Only thing it will do is it will collect a lot of dust, right? Because it's very sticky like honey. So what I thought was, well, we need to somehow create a lot of interfacial area again with a low pressure drop. And then we need to create somehow a system we can put it in there with somehow dealing with the fluctuating humidity. So I called my friend at Cornell, Yong-Ju, whose expertise in battery field, making the electrospun fibers. And I said, can you make electrospun fiber with my material kind of embedded inside? And we started looking into this. Another thing I did was I started working with Michelle Kidder at Oak Ridge National Lab. She makes this material called PIM1 and PIM materials. It's like a lot of highly porous polymeric materials. And because the structure of this, like aromatic rings around, is very rigid, and you can create a lot of porosity, but also you may not be able to see it, a lot of fluorine groups, so it can be hydrophobic. So what we thought was by combining this unique shell material, our NOMS material, making into spun fiber system, now you have filter system, we can just leave it outside, capturing CO2, but maybe less CO2 in, but reject the water. And we actually did. So this is some of the data. You can see hydrophobic behavior of the surface of these electrospun fiber encapsulated NOM system, and also huge increase on the CO2 capture capacity and rates. So let's talk about now we capture CO2. Can we combine this to make other stuff, which could be quite interesting? And we talked about that with Michelle a little bit as well. So then looking into this, I was looking into people who are in catalysis area, what they've been doing on CO2 chemical reduction. For example, electrochemical reduction of CO2, which you're going to hear about later on today. That there are a bunch of areas you have to look into, which catalyst metal you're going to use as a catalyst, and what does it look like on the morphological structure, and how about the devices and all that so on. But one thing people weren't really looking at about 7-8 years ago as much was design of the electrolyte, right? At the end of the day, you can have an amazing, fantastic catalyst, but somebody has to deliver that CO2 to you, the surface of the catalyst, in a form you can actually convert, right? So I thought, well, I have this interesting liquid material, grabs CO2 quite well. Can I make into the electrolyte? That was one of the first thinking we did. So let's think very simplistic system of two liquid fluid system. One is polymer, which I started with, right? And blended with just water, typical electrolyte. And the other one is our tethered NOMS mixed with water and then salt. So now we have two electrolyte. One is added with the polymer, which is untethered, right? And then now one with the NOMS. So I kind of hypothesized that, well, if this one can perform as well as this or slightly worse, I'll take it, right? As an electrolyte. Because the only comparison between two is that this one has a whole bunch of nanoparticle running around. And it shouldn't be good as an electrolyte. That's what I hypothesized. But then when my students went into the lab and keep measuring conductivity and viscosity, it was really weird. As you can see here, this is the untethered polymer, and this is our NOMS-based electrolyte. Two electrolyte at lower concentration. Now we are not talking about extreme high viscosity because we're mixing these with the aqueous phase. We had a NOMS-based electrolyte has higher conductivity and lower viscosity. It was really weird. So I keep sending my student back and go, oh, you must be got it wrong, or maybe data set was converted. No, it was continuously getting that data. So we took this to Argonne National Lab. Maybe something else is happening in this electrolyte system, which I didn't anticipate it. And when if you're familiar with USACs, this is the Q, which is inverse of the length scale. Generally, NOMS-based fluid system, you should not see any signal here because they're very tiny. It should be mostly here. But there were very interesting zones kind of showing. And based on different zones, we can kind of reconstruct, working with our collaborators and NIST, what it looks like, our NOMS-based electrolyte. So if you look here, in the naked eye, it looks like a clear, transparent fluid because nanoparticle is very small and it's relatively well distributed in the system. But if you zoom in, there's agglomerates about the 1 to 2 micron size. Huge, right? And then if you zoom in even further, there will be tens to 100 nanometer, some aggregates. And because of that, there was a lot more interaction than we thought between NOMS to NOMS within this fluid system. Of course, depending on what is the background electrolyte you have, it will make a huge difference in solvation behavior, structure of these polymers, and how they create the hierarchical structure in NOMS-based electrolyte. But because of that, the transport through this system is a lot more complex, and it was working for us, favoring a really good CO2 capture at the same time, hosting electrochemical reactions, which was really interesting. So now let's put it into work, right? So in each cell, we can bubble CO2, and this is the electrolyte at the bottom, the orange one, which is without any NOMs. Just typical potassium bicarbonate electrolyte. It captures CO2 very little, but because right now per-pass conversion of our electrocatalyst is not that high, we're still okay. You still have plenty of CO2 there, or you can continuously bubble CO2. But as you add more NOMs, you have a huge increase in CO2 capture capacity by the electrolyte itself, which was really nice because now you can host both CO2 capture reaction and convert reaction. And another interesting thing was our Faraday efficiency. And that was changing a little bit, kind of hinting that the way we deliver CO2 to the surface of the catalyst may not be as simple as we thought. So one way is that NOMs become the kind of internal reservoir of CO2, so that CO2 get dissolved into the bulk, and then that CO2 will be reabsorbed onto the surface of the catalyst. That's one way. Or you can actually have these NOMs deliver the CO2 to the surface of the catalyst and hovers around during the CO2 conversion. And some of the people actually saw similar behavior, changing the selectivity of the product, Faraday efficiency, if these either ionic liquid or amine is hanging around near the surface of the electrocatalyst. So we start now calling it co-catalyst, but I think there's a lot more questions and what is actually being actively converted, because one of the argument or our hypothesis we still have to figure out is that having NOMs with maybe Lewis acid-base interaction hovers around and bend the CO2 just right so that you can have favored CO2 conversion faster and also in different pathways. So we start looking into this a little more further into depth. This is the without any NOMs or additives. And two types of additive we wanted to put. One is NOMs made with a lot of amine functional groups, which means that you will have a lot of carbamates in your electrolyte. Another one was NOMs with just ether groups, which means you have weak Lewis-base, acid-base interactions. And here is the data. So you can see the first one is similar to the third one, right? Because this one is a very weak interaction between CO2 and our NOMs. So in a sense that you were able to do similar performance of your catalyst by just shuffling CO2 much better in your electrolyte. But if you actually capture CO2, most of the carbamate is not electrochemically active, so you didn't see much of the product formation. Only way you can boost this upwards will be when you heat up this system to at least 60 to 80 degrees C. But that's still mild condition. But by looking at this, I start to think that maybe we really need to focus our understanding is electrolyte and electrode interface. What the heck is really going on in that space? So I actually went to my students. I sent my students to NREL, National Renewable Energy Lab, where my collaborator, Wilson Smith, is there. And he actually have a really unique system of AFM. And this AFM has an electrochemical system attached, so you can actually do electrochemical reaction, performing that, at the same time understanding what's happening on the surface. So what we started with is just the silver foil as just this first surface, and you can measure the average roughness and average modulus and also deformation. So this is our base case. And then when we just expose that to just adding PEI, it's a very short brush of 2,000 molecular weight. And then when we measure the exactly same thing, you're not seeing this number. Maybe I should go there. So then the numbers have changed a little bit. Right? So by having polymer, the fact that these numbers changed means that there was absorption of these PEI on the surface of the silver foil. So it gets much more deformation and then lower modulus. So let's look at this with our system. So this is the case with just topography and then 3D and then modulation, and this is adding just PEI. And then let's take a look. This is only PEI in water, no other ions available. And then as we apply potential, now going down, we start to apply the potential. And what happens to this? And then what we found out was that all this polymer, which was kind of absorbed onto the surface, because electrostatic interaction, you start to collapse onto the surface. So that will be so definitely when you're trying to use this model to understand or explain what the heck happens during the electrochemical reduction, you won't be explaining well. How about the system we are really talking about here? Slow acting. Okay, there we go. So what if I saturate the entire system, put the supporting electrolyte as well as the saturate with the CO2? Now there's a lot more stuff happening here because there's a CO2 interaction with all these functional groups, and there's ions running around and sorbation happening and all that. And then now we apply the potential. And there was almost no change in the system. So then now we understand that there is a lot of permeability, and that electron double layer has very interesting behavior of diffusion, movement of ions, and it facilitates a different way of converting CO2. So what we should really look at, I guess eventually, for the combining CO2 capture and conversion is that somehow we need to start with not only power plant CO2, but a wide range of carbon dioxide. It could be directly from air, or even the buildings, or ethanol plants, or cement plants. And all these CO2 streams bring different challenges and opportunities. And we should really thinking about not individual silos of a catalyst development, electrolyte development, or CO2 transport problems, none of those. Now, biggest problem it will be at the interface, how to connect things together. How can I capture CO2 and deliver the CO2 to the surface of the electrocatalyst, or how to combine electrochemical conversion with the biological pathway of upgrading that to C2 plus molecules, right? And we should also ask the question, these are some of the commodity chemicals we know, because we usually make this based on petroleum feedstock. Are they going to be same commodity chemical for the future? These are all big questions we need to think about to really have a circular carbon economy. Finally, I want to tell you a little bit about clean energy transition, just a few slides. I think one of the challenges we've been talking about fossil fuel is the scale, right? If it was just a little bit of CO2 problem, we're not going to have global discussions on why and how we need to attack these carbon management issues, as well as climate change issues. So when we talk about climate change, is more on the carbon emission. It's kind of an accepted kind of field. And then we've been talking about, to solve that, we need to have clean energy transition to more solar, more wind, and so on, or biomass and all that so on. Good, right? Is a clean energy transition really green? Have you ever thought about it? Right? I think we assumed it was green, and then we put the color green thinking the green is a good thing, right? So people in the United States start talking about what is really needed to make that transition happen. A lot of rare earth elements. You heard about issue with the critical minerals, rare earth elements, right? And now we even broaden in that scope. Not only rare earth elements, we have to call it energy relevant critical minerals. Energy relevant is a little broader. So for example, not only rare earth, we need to have more lithium, more copper, more nickel, more cobalt, and all of those. And we need to get them more sustainable way. But how do we get them now? Like here. How many of you been to mining site? Few, right? I was told on the way here that you guys have quite a bit of mining here too, silver, right, and many other things. So this is the Serpentine mine in Vermont. This is one of the many, and this is actually a nickel mine. And the concentration of nickel was very low. And this one actually is the copper mine, which is one of the largest in the world, the biggest in the United States. And you can actually see this from space. So big, right? So although we are using a lot of cell phones and everything else, you don't think about it, these are not this heavy. These are very heavy, right? Because all these rocks are behind all the devices we actually use. So concentration in cell phone, maybe in average, a copper is about 16%, let's say, depending on your cell phone. And here, this is one of the batteries, has a lot of nickel in it, right? So let's think about how much is the nickel and copper concentration in these two piles. Can you imagine? I was really surprised when I heard the numbers. Only 0.4% in copper ore, and then we only have 0.28% nickel in this pile. We literally move mountains every day to have clean energy transition. Do we like mining? Are they sustainable or green? No, right? So if you really want a clean energy transition, you need to develop sustainable mining process, a whole new way of doing even urban mining, recovering things out of the end of the life, and which leads to very interesting chemistry and chemical engineering problems. How do we do all these separations? So one of the areas a lot of research many of us are going into is this one particularly, and this as well. But this is interesting because this is magnesium silicate minerals, majority, right? Because there's only 0.28% of nickel in it, right? So after taking out the nickel, you have a huge amount of silicon-based ore, which has a high concentration of magnesium. You can actually make an artificial limestone-like material fixing CO2. So a lot of us start thinking about, can we do metal recovery, energy-relevant metal recovery with the carbon sequestration in one system? So many of us are looking into that. So in order to do that, all these piles of rocks has to be digested and putting all the nickel or even additional nickel, but also magnesium and other things into the solution phase. Okay, now there is a fundamental question. If instead of giving you solution with only copper in it or nickel in it, electrochemical separation of that system is not that difficult. That's what we've been doing in the past in the mining system. But what if I tell you there is a system now have a huge concentration of alkaline earth metal, like calcium and magnesium and many other minor components, and I want you to just separate out nickel only? Very different question, right? And very hard one. So it's always easier to go back to nature because they always master everything very well. So we start looking into different ligand systems. So this is a current mining, and we need to have much greener mining, and there are many questions how to tie the carbon sequestration and all those things. I think this is the problem for next generation and current generation. So what we end up doing was we decide to make a structural ligand. By structural ligand means that we're not going to only target the binding energy to separate the metals, but also create the right size pocket so that we can really harvest the metals we want, either REEs or the specific metals. We can make it with a different binding energy, and what we saw was by doing so with the really making different size cavity with different binding energy in that system, this is the comparison of cerium with the sodium, calcium, and magnesium. We put just a whole bunch of other ions and see the separation. And we were able to really separate well in the presence of a wide range of competing ions. And this DFT calculation shows that the cerium is very snug and then binding to all the sites we created within scaffold structural ligand system. But calcium and magnesium, you see that there's a lot of loose ends, so they just goes in and out. So these are one of the things I think we can also learn from our GNOME system, how to tune the structures and chemistry to do the better separation. So finally, I would like to conclude saying that I think the carbon management, during our meeting at CIFAR, we had a lot of this discussion, and Carlos, you were there too. In fact, that a lot of carbon management technology is not going to have only one single silver bullet, right? We really need to think about what makes sense to Mexico, what makes sense to US, or what makes sense to combined effort, right? All these questions bring very different challenges, but opportunities at the same time. And we should start thinking about how to electrify instead of using thermal fossil energy to make our commodity chemicals to create the whole new circular economy. But whatever you do, let's start to make our system boundary a little bit bigger, including the Earth within our system boundary. Here are people who actually do a lot of great work, my students at Columbia University and the funding agencies. And thank you, and I'll be happy to answer questions.
Discussing at the CIFAR meeting these 2 past days ago is that maybe in top of finding all these marvelous chemical solutions, scientific solutions, we also have to do, as you were saying, a change in our lifestyles. We need to do that also. And that's going to be different changes in different places, maybe the same way that we will have to do several different things in different places because of the local different necessities and styles. Please, someone has a question? Please, let's start with Diego.
Thank you, Lisa. Wonderful talk. I was wondering, kind of combining the first two parts of your talk, so if it makes any sense to try to make a capture system that regenerates using electricity instead of heat. I guess in the second part you try to directly convert it, but it seems like electricity could be way more efficient than heat because we can, I guess there's fewer thermodynamics constraints and you can be way more efficient if you were to use some energy potential to release the CO2 instead of heat.
Great question. So I didn't show some of the data because of time constraint, because I wanted to cover enough stuff so that I can attract the potential postdocs. But that's one of the good research areas. So especially when we talk about direct air capture or direct ocean capture. So when you talk about CO2 capture from power plant is in the business of making heat and power. So you should use heat and power to do solvent regeneration. Makes sense, right? There's a waste heat lying around, hopefully, so that you can do solvent regeneration. But let's say you're doing direct air capture or direct ocean capture. More likely, you're not going to be near the power plant, right? Why would you do direct ocean capture and air capture right next to power plant? Which means, what is the easiest energy to put it there is, interestingly, renewable energy. And eventually, we'll use renewable energy to green entire grid anyway. So now there's a question, right? Or the CO2 capture technology or conversion is downhill capture, but you need to put energy in to either kick it out or convert to something else. Until now, we usually use heat to do the conversion, right? Or regenerate. What if it has only electricity? What would you do? Now we call this a non-thermal energy transfer, right? There are so many ways to do it. So let's say in our or even NOMS material, where CO2 is bound is where carbamate is, for example. But in order to release the CO2 from carbamate, we heat up the entire reactor. As a chemical engineer, we love the word isothermal, right? A steady state, right? So in order to do that, we heat up everything to the same temperature. But what is the minimum amount of energy you want to put in? If we can zap only where carbamate is and nothing gets heated up, you can actually do CO2 capture and solvent regeneration at the exactly same temperature. That's the extreme ideal case. So we started looking at the easiest way of doing non-thermal energy transfer. I'm not an electrical engineer, right? So what is the easiest one? Everybody knows how to do this. Microwave, right? So we start looking into microwave, right? So if I can design our CO2 capture material have with microwave active material certain spots, but rest of the stuff can be microwave blind, like transparent, then maybe we can only heat up their location, right? So we can zap. And we were able to do that. So instead of having half an hour to an hour for solvent regeneration, we love microwave because we can heat up things fast, right? It was reduced by like 1 or 2 minutes. You can regenerate most of the CO2, it released back. And also the temperature of 2 reactors, capture reactor, like if we capture CO2 ambient temperature, you end up regenerating with maybe 10 degrees higher in the entire reactor. So definitely there's an extreme high potential of energy saving, but I think now we have to work with electrical engineer or other people who understand how to design microwave reactor better. But very interesting area of research.
Hi, thank you very much. Well, my question is how possible, if it's possible, to integrate an electroswing process that was developed in MIT that they're fixating this carbon dioxide molecules into the catalyst. So how easy would that be just to integrate with an electroreduction system in order to obtain more substances? I believe that there's a pathway there, right?
So integration of carbon capture to electrochemical reduction, or?
The electroswing process.
Oh, that, yeah?
Yeah.
that one is quite unique, right? And then when we first started Alan Hatton's group, we were like, oh, where are you going to get all the electrons, right, to do this? But now we do, apparently, right? I think that's really interesting area of research because you're basically using the chemical potential to do all the regeneration. This is one way. And Alan's approach is nice because it's all in the liquid phase. You just need to pump things around, similar to flow battery, in my opinion. So that works. I think next generation of what Alan should do, electrochemically driven pH swing and all that, I think they CO2 regeneration, they should combine the conversion. I think that would be a really good potential for sure.
Yeah, because like the efficiency is better, like at high level temperatures, right?
Yeah, that's
Okay.
one way, yeah. But I think one of the things is I would like to say CO2 capture and conversion should be integrated. I don't think we can go directly from air all the way to conversion in single reactor, just because amount of air you have to process so much. So more likely you have to pre-concentrate and then you do that. We should be able to design a reactor actually do that at the same time. Good question.
Thank you, Dr. Park, for a nice presentation. I am Atit from Material Research Institute. So actually, we are seeing that nanotechnology is offering so many advantages, for example, right now. My question is, if we are going to employ, for example, nanoparticles, nanowires, porous structures, MOFs, they are quite expensive to produce sometimes, and we have to use them in the plant, for example. So what about the cost relation and the final dumping of these materials after some use? Can you comment on that, please? Thank you.
Sure. I think I heard enough since a little while. I think there are multiple things I worried about. Cost, for sure, right? I mean, cost is expensive. If it is expensive, it's a problem. But one of the biggest challenge for even cheap or less expensive liquid solvent for CO2 is how robust they are. So if you are able to run only 100 cycle versus a 10,000 cycle, there's a huge difference. So Petronova project, they never published, but what I was told was they thought it would be robust to running the amine solvents for many cycles. The way you fix that, if there's a degradation, you cannot pin out which part of the solvent is degraded. So you end up taking some spent solvent out and you have to put fresh in so that there is always a minimum amount of degraded material, right? That makeup amount was much more than they thought. So the cost of your sorbent or liquid solvent has to go into the noise. Like it shouldn't be a huge portion in your operating cost, and it became that, which means that we need to improve the thermal stability of that liquid solvent. Same thing with any other materials. So as long as you can run it for many cycles, cost should go into the noise. Bigger problem. I think a lot of times we work on nanoparticles or nanowires or any of these, we don't think about the environmental impact of these things, right? Because if you're doing direct air capture or kind of these are exposed to the environment, we need to make sure that there's no exposure of these to the environment. And because of that, although we start with nanomaterials, we encapsulate them in the fibers can be much bigger. Maybe we'll end up with that just because the environmental concerns, but very good questions.
Hi, hello. First of all, wonderful job. I'm personally amazed by how complicated the industry can be. But for us, the new generation of I don't know, chemical engineers, everything and that stuff, I want to ask, how did you get the process of all of these all of these things, all of the reactors, the industry, the electrochemical process. For us, how can I take all of these questions, this uncertain process to be applied? How can we get to know what we are wanting to change in the world? How was the process of thinking all of this?
This is a very tough question, right? Almost philosophical. So how do I get inspired by others in a sense, right? When you think about this, because I have my chemical engineering expertise in the narrow area of hybrid materials and reaction mechanisms and all that. But then, as you can see, there's a multifaceted angle of my research. I think that is happening by networking and meeting with other experts, right? But even if, to me, this is how I explain to my students. You can be in the room with amazing expert on amazing things. If you don't know how to connect yourself to that person, there's no collaboration or no new science. So sometimes what I usually do, or often do, let's say I go to American Chemical Society meeting. If I have like 10 minutes left over between meetings, I go into random room. And then I like to make a connection between what I know versus what the heck the speaker is talking about. More and more you do, thinking that how I can kind of make a bridge with others, you become a lot better to ask a meaningful question for your research while enriching, bringing other expertise. And I think there are many ways to go at it, but that's how I do it usually. But there are so many questions, and I'm hoping that you will come to maybe Colombia and ask those questions along with us. Thank you. Thank you.
I want to say two things about this. Incidentally, we saw the pictures of effects of mining. Incidentally, we have an exhibition of photographs here at the Faculty of Chemistry, an exhibition of photographs of effects of mining in Mexico City. You may want to go over. I will let you know where they are. They are very, very tough, at least. That's one thing. The other thing is that I have not said what CIFAR is so far. CIFAR is the Canadian Institute for Advanced Research, and they are visiting us in Mexico. CIFAR is Canadian, yes, but the people that belongs to CIFAR are from very different universities in very different countries around the world. They are visiting Mexico because they are trying to, see what Mexico has to offer and start collaborating with us. That's the reason we have them here, and we have had their meeting in Mexico these past two days. Okay, let's move on. Our next speaker is Professor Fraser Armstrong. Fraser Armstrong is Emeritus Professor of Chemistry and a Fellow of St. John's College. His interests are in biological chemistry, bioenergetics, and in the mechanisms and exploitation of enzymes related to energy production. What I want to read about this is he travels widely, giving invited lectures on topics including catalysis, bioenergetics, and renewable energy. He is co-editor of Energy Beyond Oil, which focuses on alternative energy generating technologies. Professor Armstrong, welcome to the chemistry school.
Okay, can I work that moving? Okay. So I'd like to thank the people who invited me here. It's a great opportunity to extend a meeting of CIFAR, which I've been attending for the last 2 days. I'm going to talk to you about a new way of studying and exploiting enzymes. And can I just ask how I move this on? Oh, it's self-evident, I think. So the technology that I'm going to talk about to you is very new. We call it the electrochemical leaf, and the reasons for that will be evident throughout my talk. But it's a way of running multiple reactions catalyzed by enzymes. We call these enzyme cascades, where the product of one enzyme is the reactant for the next enzyme along the chain. And the little emblem there, this is prepared or made by one of my postdocs. Can we move in? No, it's not advancing, so I don't know. Yeah. Yeah, can I have some help? Yeah. Yeah. Okay. Right. So these are the people who worked on this project. There's a relatively small number of them. Claire McGarity has been a postdoc. Parvin Siritana Rakul, he's now a postdoc in Liverpool. Giorgio Morello, he works for a biotech company in Cambridge. Lei Wan, Bei Shen Cheng, and my student on the right, Ryan Herald, who's still busy at this time back in Oxford carrying out experiments while I'm here. I'd like you first of all to look at this. You won't be able to make out anything on this slide at all. This is a copy of a book on metabolic pathways, and these. See if this will work. Yeah. So all these, you can see there's probably about 1,000 or so reactions here, connecting different natural product reactions to another, probably involving at least as many catalysts, enzymes along the way. And when we normally study enzymes in a biochemistry lab, those enzymes are usually quite dilute and they're in aqueous solution. And that's not the way that enzymes are in a living cell. Enzymes in a living cell are very crowded, and they're crowded into compartments. And they're crowded into compartments such as carboxysomes in bacteria, peroxisomes, the mitochondrion, and the chloroplast. And the concentrations of enzymes, different ones which are catalyzing reactions along a cascade, can be very high indeed. As an unrelated example is hemoglobin in our red blood cells is about 5 or over 5 millimolar concentration, and the molecules almost touching each other. They're so concentrated, and that's very different from the way that we normally study enzymes in a lab. So how can we find a technology or build a technology which uses the crowdedness of enzymes which we achieve, which we know exist in a living organism, and now extend that to a material? Because what I'm going to explain to you is how we activate and control enzymes inside a material. And this allows us to both make pharmaceuticals and study enzymes in ways that we've never been able to do before. So, this is a very simple concept. Let's say I have a block of bricks for building a house, and I take these one at a time, and I throw them onto the floor, and I form a pile of bricks. Now, what you would immediately realise is that this is not going to make a nice wall. It's a big pile of bricks with gaps between every brick. What would be the size of gaps between the bricks? It will be largely dependent on what size of the brick was. So we can roughly confident that two bricks which have a And that's very important because if we chose instead of bricks, nanoparticles, and those nanoparticles have dimensions of the spaces of in biological compartments, and little more than the dimensions of enzymes themselves, we should be able to trap enzymes within the gaps. Now you might think at the moment, what use is that going to be? Well, there's a trick here which I'm going to explain in the next few slides. So let's first of all consider how we would make such a porous arrangement of nanoparticles, and we're going to do it on an electrode. We're going to put it on an electrode material. So what we do here is to take the conducting metal oxide nanoparticles. Indium tin oxide nanoparticles, of course, are commercially available, and they're used to make screens in and various sort of technologies, optico-electronic technologies. And if you take a suspension of indium tin oxide nanoparticles, or you can do it with fluorine tin oxide and aluminum zinc oxide and so on, these are conducting nanoparticles, and that's the important thing. They're going to conduct electricity. So we have a suspension of these nanoparticles in dry acetone, and we add some iodine. Now what the iodine does here is it causes the nanoparticles to get protonated, and they migrate to one of the electrodes. So we're going to make an electrode by electrophoresis, and we're going to deposit a layer of metal oxide nanoparticles on the electrode that we're going to use now to study enzymes. And depending on the time that we carry out that electrophoresis at about 15 volts, we build layers which extend up from 3 microns to perhaps 6 or 7 microns thick. And these are very stable layers. And after we've done this, we can study that layer by various techniques. This is some scanning electron microscopy that I show here, where you can see you've built yourself a sort of sponge. You've built a layer which is very porous indeed, but it's electrically conductive. So we now use this a modified electrode to put enzymes, to load enzymes into. Now a little digression here, and this is nature's major hydride carrier, hydrogen carrier. So this is a nicotinamide cofactor, and the nicotinamide cofactor is here. You might see it even better. The resolution is on this screen is not quite so good. But nicotinamide cofactors differ amongst themselves in 2 ways. They can either have a hydrogen atom here or not. So if they have a hydrogen atom attached, this is the reduced form of the nicotinamide cofactor, NADH or NADPH. And whether it's NADPH or NADH, the P is the phosphate group which attaches to this sugar ring. Now, nicotinamide cofactors are 2-electron carriers. They're more or less obligatory 2-electron carriers. The radical is extremely unstable. And nature uses nicotinamide cofactors as wonderfully high-fidelity hydride carriers. This is nature's version of borohydride, or aluminium hydride ion. That's the way that we must think of it. But unlike those chemical reagents, these are highly specific. And in what happens in nature is that electron transfer systems, such as photosynthesis, which are able to make hot electrons, very energetic electrons, they transfer electrons to a flavin cofactor, and flavin cofactors can do 1 and 2 electron transfers. And then the flavin cofactor is able to transfer a hydride, which is effectively a proton and 2 electrons, to make the reduced nicotinamide cofactor. One such enzyme I'm going to mention is very important in our work. It does this extremely well. And then numerous enzymes, thousands of them, which are known as dehydrogenases, catalyze myriad reactions across the whole biological world, in which that hydride is now transferred into organic chemistry. So basically, this is going to be the organic chemistry which occurs inside a cell whenever it is driven by an oxidation or reduction process. Now, this is a very important enzyme. It's been largely forgotten about for many people more interested in sexy enzymes that capture sunlight and turn it into electrons. But this is a photosynthetic enzyme, which is perhaps the mother of organic chemistry, or the mother of biological chemistry. It's called ferredoxin NADP reductase. And what I show on this slide is the way that this enzyme interacts with its natural electron transferring partner, a ferredoxin. And this enzyme occurs in all chloroplasts. It's present across all green plants. It's really very universal. I just showed 2 versions here. On the right, this is a cartoon version. This is FNR, ferredoxin NADP reductase. This is the flavin group. This is a nicotinamide cofactor bound. And next to it, in a surface charge model, is the ferredoxin, which forms a tight 1-to-1 complex with FNR. I show the reverse over here because this is the ferredoxin. It's got an iron sulfur cluster which discharges 1 electron at a time, and there's the FNR. And this complex is formed by a very polar complex interaction, largely between a negatively charged surface on the ferredoxin and a positively charged surface on the FNR. And most importantly, for every 2 times a ferredoxin molecule binds and leaves, it charges up the FAD so that it can pass a hydride to nicotinamide cofactor. So, this is another way of looking at that reaction. This is the FNR. This is the flavin cofactor. It's an FAD, flavin adenine dinucleotide. This is the ferredoxin, and there's the iron sulfur cluster. And there's an electron tunneling distance of less than 6 angstroms that the electron has to move. And as I said just now, it does that twice for every NADP molecule which is formed. And this is the birth, the birth of all the redox chemistry that happens in photosynthesis. So, this molecule of FNR is a small protein. Its molecular weight is less than 40,000. We now go back to the electrode, because we've made our electrode, we've washed it, and then we introduce FNR. This is actually very simple, because I just take my electrode. Good. Thanks for reminding me. Yeah. Okay. So it can be a piece of titanium foil, or it can be a small electrode. And what I do is I take a pipette tip, and I have some FAD solution. It's a very beautiful yellow protein, and I just paint it across the surface of the electrode. Just dab it on. The enzyme now soaks in to the nanoparticles. And remember, these are conducting nanoparticles. And on the left here, I hope many of you are familiar with electrochemistry or with cyclic voltammetry. because I can give a very brief description. This is the electron transfer reactions of ferredoxin NADP reductase. What you have to look for here are these peaks. You see, there's a large area of capacitance because, of course, the ITO layer is very porous. It's got a lot of capacitance. But just here, if we start here, if you follow my tracer here, I'd be going to reducing potentials back to oxidizing potentials, and so on. I can do this hundreds of times. Every time I do that, at this particular potential, at about minus 0.4 volts, I put 2 electrons into the FAD cofactor. And then I go back to the baseline, and then I take the 2 electrons out. If I subtract that capacitance baseline, I get this here. Now, what is important here is first of all where the peaks are in position. So these peaks are averaged at the reduction potential for the flavin cofactor in FNR. This is excellent. It's exactly what's been reported for 20 or more years. The peak width of 57 to 59 millivolts are also very important. If this was a 1 electron reaction, I'd have a peak width of 90 millivolts. If it was a concerted, absolutely concerted 2 electron reaction, this would be 45 millivolts. It's somewhere in between, you see, because the radical on the FAD cofactor here, has sufficient stability to separate the 2 electron potentials out, just enough. This is exactly why it works so well in nature. Now, if you go to the right-hand side, what I've done here is I've taken these background subtracted voltammograms, but now I've looked at what happens to the area as I go from pH 6 or 5, sorry, 6, 7, 8, 9. What you notice is that obviously the peaks get smaller. That's not the most important issue. The important point is if you were to look at the charge under one of those peaks, and of course the charge tells you through Faraday's law how many active sites, how many flavin sites must be undergoing electron transfer. And it turns out that your coverage as a function of the area, the geometric area of the electrode that you chose, at pH 9, this is over 500 picomoles per square centimetre. If you had a monolayer, it'd be about 5 picomoles. It's 100 monolayers here. The enzyme has gone deeply into the pores. And you can even work out a concentration now because you can take a very good estimate of what the pore volume would be, and you end up that the enzyme concentration in molarity is over millimolar. So you've really got to a very high concentration of enzyme there. Well, so far we've done nothing. All I've shown you is that you can look at an enzyme by electrochemistry, and I've been doing that for 40 years in my career. But there's something special about this one because, whoops, I went too fast there. Yeah, right. I'm not showing the voltammogram yet for what happens when we put NADP into the system. What I'm showing you instead is what happens to the current which I'm measuring at a certain potential as I have placed nicotinamide cofactor into the solution. In this case, I think it's about 10 or 20 micromolar. Doesn't really matter that much. But what I'm doing here is I'm introducing to the solution. We've already made the FNR electrode. Right? I'm introducing into the solution now a second enzyme. And this enzyme is able to use the nicotinamide cofactor, which has been reduced by the FNR. And this is an important experiment because I've introduced that enzyme only in a very dilute quantity into the surrounding solution. And I'm monitoring the catalytic current that emerges in the presence of the reactant for that dehydrogenase. So I do a little bit of explaining here. ADH. In this experiment, I've got an alpha. I've got an alcohol in the solution, a secondary alcohol, and I've loaded the enzyme with FNR. I've got a small amount of NADP in solution, and the catalytic current, what I'm seeing here is the oxidation of the secondary alcohol to the ketone, and you notice that the current grows over the course of about an hour, very, very slowly. The catalytic activity, which is the current, you must remember current is rate, that's the rate of the reaction is occurring. The catalytic current rises almost exponentially in this case. No, there's no activity straight away. The catalytic current depends on the second enzyme also now going into the pores of the film. So it joins FNR. And likewise, you see for other enzymes, this was a very, oops, that's it. So this one down here, this is a very slow enzyme. This is a malic enzyme. This converts pyruvate to malic acid. This is a reductive aminase. What we're seeing here is the emergence of catalytic activity as we add a second enzyme to join the first enzyme, FNR, in the pores, in the presence of NADPH, which can recycle in the pores, and it's trapped within the pores. So this is then an idea of what you now see, and you can see it fairly routinely. This is the secondary alcohol at the top, and an alcohol dehydrogenase will convert that into the ketone. This is the sort of system as we envisage it in the pores. You've got FNR, it's recycling nicotinamide cofactor, and you've got an alcohol dehydrogenase nearby. And you now observe the cyclic voltammetry of an alcohol to ketone into conversion. So this is an organic reaction. You don't normally see this with electrochemistry at all, because by any normal electrode, this is electrochemically so irreversible that it doesn't happen. What you see here, under the right conditions, and this is at pH 9, at pH 9 the rate of oxidation of the alcohol to the ketone is about the same as the reduction of the ketone to the alcohol. And so this is oxidation, this is reduction, this is the reduction potential for the alcohol to the ketone conversion. So you get that directly out of the experiment. If I go to lower pH, the reaction becomes biased in favour of the ketone to the alcohol. All of these experiments are done with a one-to-one mixture of the alcohol to the ketone in the solution. And you've got just a small amount of nicotinamide cofactor here, about 10 micromolar. So this enables us, and this I'm jumping ahead here, to build a technology in which you can choose what enzyme you want to put into the pores alongside the FNR, and you can then build cascades. For different purposes, such as the production of high-value chemicals. And the way I represent these here is as transport maps, like a metro map. It's a very convenient way, because I must say now, it does not matter that the second enzyme, which would be E2, a dehydrogenase, is close to the first enzyme, E1, which is FNR, because diffusion is so fast within the pores that as long as it's reasonably close, it will couple, and it will couple very effectively. And so hence I make these maps now like urban transport maps, because the product of E1, so the product of E1, which is, in this case, would be oxidized nicotinamide or reduced nicotinamide. Don't forget, I can go both ways now. Nature can't go both ways, but electrochemically you can. the product will always find E2, and then if a reactant for E2 comes in, you get the product. So this would be typical. This is the smallest cascade we can make. It's just as I've shown you with the alcohol dehydrogenase. This is a long cascade. This has got a total of 5 enzymes in it. I'll show you this. I'll show you this one later. But it fixes CO2 at this point here. It hydrates at this point, and it adds ammonia at this particular point here. And then another one. This is the reduction of a long chain carboxylate to an aldehyde. That requires ATP as well. But that's no problem because you put kinases into the pore, and now adding a phosphate carrier like phosphoenol pyruvate, PEP, what you now do is you build ATP recycling into a system that accompanies the electrochemical recycling of nicotinamide. So I now have enzymes and enzyme cascades of possibly reasonable complexity, all under control. I can run them just like I can a car. And so I took a photo of my car. I was so pleased to make this analogy. But the analogy is really rather neat because first of all, the reaction in our hands is bidirectional. I can oxidize and I can reduce. It's simply where I set the potential. So the electrochemical leaf has a forward and reverse gear. It's got a throttle. Now the throttle is what voltage I apply. You know, if I apply more oxidizing potential, I can get the reaction to go faster up until the time it's then limited by another enzyme reaction. I can stop. I can look at the rate, or the rate is the current. I can find out the number of miles or kilometers or moles in our case that I've done, because this is the odometer, this is the integration, and I can navigate. There's my house there, but I can know exactly where I am because I can look at the electrochemistry. I can see what I've got in the system. So I'm going to move on very quickly in a minute. But first of all, I'm going to look at some of the enzymes that we've studied so far. They're very big. It doesn't make any difference. The interesting thing is enzymes enter the pores spontaneously. They go into the pores and they stay there. All you've got to do is paint them on, or you can introduce them from dilute solution. So enzymes that we've studied include alcohol dehydrogenase. You can see roughly what the dimensions of them are. Isocitrate dehydrogenase. This is FNR here, and next to the name of the enzyme, I put the maximum concentration that you could ever achieve in a solution based on the size. So the first one is based on a close packing, a crystallographic packing model, and the second one is based on a close packing model assuming spherical enzymes. So that's a pretty small enzyme, adenylate kinase. Aspartate ammonia lyase, this puts an ammonia into the pyruvate kinase, fumarase. These are not redox enzymes. You can notice that there's very few of them are redox enzymes at all. It doesn't matter any longer because we've made all enzymes of interest to us now electroactive because everything is channeled in the pores, and so fumarase becomes electroactive because we can see its action through the electrical current if it occupied a pivotal place along a cascade. So this was an example that we felt we had to do to scale up. So we're putting the ITO nanoparticles, we're depositing them on titanium plate. And this is titanium foil. So it's the sort of thing when you look out your aircraft wing, your aircraft's wing's made of titanium, and this is titanium foil. You coat it both sides with indium tin oxide nanoparticles. You make pretty big electrodes in this way. You paint them with enzyme. You can use very little enzyme in this way, and this is making a chemical in about 36 hours. I think it's only a couple of grams of a chemical, but by most people, most chemists scale up electrochemistry. It's not too bad at all. So this is just a simple reaction. We're using, as enzyme number 2, we're using glutamate dehydrogenase. Enzyme number 1 is FNR. This is the course of the reaction, you see. You start out at a current here. We're electrolyzing a solution which is about, what's the concentration here? Anyway, we're making about 20 millimoles of product here. And as you go through the reaction, you see the current fairly constant. When you get to this, you can look at your integration, and you can see, well, I'm halfway through now. You know, you just work out the coulombs that you pass. This is the halfway mark. This is the 75% mark. This is the 90% mark. And as you can see, you're now tailing off because you're running out of the reactant. So that's really a proof that you can scale up to at least half-liter quantities there. This is an enzyme. This is an enzyme system where you now you use an alcohol dehydrogenase from 2 different organisms to carry out and manipulate stereo inversion and deracinization. So the trick here is if I take a racemic mixture of this secondary alcohol here, and let me see. Let's just go down to here. So I've got two alcohol dehydrogenases here. One is specific for the R form of the enzyme, and one is specific for the S form of the enzyme. The R-specific alcohol dehydrogenase is not a zinc enzyme, but it depends on magnesium ions for activity. So if you have both of these enzymes present at the start, and you oxidize, you apply the potential to oxidize these to the ketone, and then when you go back and do the reducing potential, just before you do it, you add EDTA. And EDTA now inactivates the LK enzyme. This is based on the organism it comes from. And so your only enzyme working on the return reduction is the S-selective enzyme. And so you make a pure mixture out of that. It's a very simple experiment which we published last year. This is an example now of a long cascade. And so what we're doing here is we're interconverting pyruvic acid, which is this thing here, and we're making aspartic acid. And so in order to do this, what you need is first of all CO2, but we don't use CO2, we use bicarbonate in solution, and we put another enzyme, this is E2A, carbonic anhydrase, we put that into the pores as well. So we load that in. That provides the CO2 for this reaction. You make malic acid, which is using the nicotinamide recycling, and then fumarase dehydrates this to fumaric acid, and then finally the ammonia aspartate lyase adds ammonia to the fumaric acid here. So we've got ammonia addition, water, CO2 and reduction, and it's bidirectional. You can do either way. It's very easy. And despite the fact that that's quite a long cascade, the reaction is electrochemically reversible because the axis, the current plot, is cutting through the axis at this very sharp point here. And this is something I felt all along throughout years of doing this sort of experiment. The enzymes, in electrochemical terms, reduce the overpotential to astonishingly small amounts. And what we see here is that the reversibility of electrocatalysis, the efficiency, is propagated even out to non-redox enzymes, simply because you've got them tightly channeled in the pores to an electron transferring enzyme. So in the next case here, this is what we're doing here is we're using an enzyme that requires both NADPH and ATP to work. What this enzyme is doing, I'll don't think you can see it very terribly clearly here. And this is actually an animation which I can't run, but it's quite neat because it shows the whole thing working. As I apply reducing potential, I convert the long chain carboxylic acid now to an aldehyde, which is using ATP at the same time. Now, carboxylic acid reductase it turns ATP into AMP, and the AMP gets quite firmly bound at the end of the catalytic cycle. So it's important to remove the AMP to allow the next cycle to go. And it's working there. So I didn't know I had to press it twice. Anyway, but that's an animation which I use very easily to show just how easy it is to study very complex systems. I move on to the next thing here. These are cyclic voltammograms in which we're simply charging the whole system with just AMP, right? So it's just AMP involved, and AMP always contains a tiny trace amount of impurity ATP. And so what you can do here is that if you supply the phosphate transfer agent, phosphoenol pyruvate, into the system, eventually you can prime the system, because the tiny amount of initial ATP will grow with time as the reaction picks up speed. And these experiments were interesting because we worked out which of the two kinases, whether it was adenylate kinase, which makes ADP from AMP and ATP, or pyruvate kinase, which converts ADP to ATP, was the most important. And it turns out here, you can't really see this very effectively, but the most important of those two kinases is the adenylate kinase, because it is needed to help remove the AMP from the carboxylic acid reductase at the end of the cycle. And what you see here over the course of time is that activity building up. So this is with the low amounts of kinase. You see it's very slow. This is over about an hour here. This is hours. I'm putting pyruvate kinase in. Here I'm uploading instead. I'm biasing in terms of adenylate kinase, and here I've got both. And the reaction becomes charged up extremely quickly now as we do that. And so this is a system where we can, under such conditions of crowding, it's important to make sure we remove a product from an enzyme reaction, because often the crowdedness and the porosity will hinder the reaction unless we're able to move it on down the line quickly. So in the last part of my talk, I'm just going to talk briefly about this enzyme called isocitrate dehydrogenase. And I've been working on this enzyme with my colleague Chris Schofield, who's interested in isocitrate dehydrogenase variants, which are responsible and underlie various forms of cancer. And isocitrate dehydrogenase catalyzes the conversion of deisocitrate to 2-oxyglutarate and CO2. And what I show here are some voltammograms of that system. E1, of course, is FNR. E2 is native isocitrate dehydrogenase. And these are some voltammograms which show that, given you've got the right ratio of your isocitrate to 2OG, it becomes a reversible electrocatalyst as well. This is the reduction potential for under the adjusted for concentration for the 2OG isocitrate system. But this is just showing that it works. This is now a series of experiments that enables us to work out how much of the second enzyme that we have in the pores. So remember, we can determine the amount of FNR simply from the area under the integration. But how do we know the concentration of the second enzyme? Well, isocitrate dehydrogenase crystallizes with a molecule of NADPH bound. And it carries that into the pores with it. And so what you can do is that you can run cyclic voltammetry at various scan rates with just the NADP, which has been carried into the pores of the electrode, nothing else added whatsoever. And in this experiment, we haven't even we haven't added any additional NADPH until the very last point here. The upshot of this is that if you take this voltammogram, which I showed earlier, and you measure two things, you measure the peak positions as the function of scan rate, and you measure the area under the curve as the function of the scan rate. And what I do is I show that here. This is now the coverage as a function of the scan rate. And you can see that, really speaking, the coverage ought to be independent of scan rate, providing all the electrons are getting to where they need to be. And that is indeed the case when you have just FNR itself loaded here. So this is going up from about 1 millivolt per second up to about 40 millivolts per second. It's constant. Now when you co-load FNR and isocitrate dehydrogenase, okay, well, your coverage is a lot lower now at high scan rates, but it rises at low scan rates. And what you're seeing here, you see at high scan rates, the electrons are going only into FNR, and the time is not available for the recycling of the NADP within the pores to the isocitrate dehydrogenase. As you slow the experiment down, what happens is that you build up your number of electrons that you're able to transfer, because you now also include the NADP, which is there. And if you do a mass spec experiment before on the enzyme to determine how many molecules of NADP you've got per isocitrate dehydrogenase, then you can relate the area difference here to the amount of isocitrate dehydrogenase that you actually have. And if you do what I call a trumpet plot, where you measure the peak positions as a function of scan rate, at high scan rates, the average peak position is corresponding to the ferredoxin NADP reductase, but at very low scan rates, when you get coupling to the IDH and you get coupling to NADP reduction, the average potential, it's not terribly clear here, I'm afraid. The average potential is now that of mostly of NADPH. So you can get a lot of information from this experiment, this type of experiment, because you can compare. You can now add isocitrate to the system, and ask the two questions. First of all, if I added just increased amounts of NADPH into the solution, and watch how the current rises, the peak current rises with NADPH concentration, it rises something like this. You see, even when you get to about 10 millimolar here, I'm still not saturated out. This looks awful. It looks really bad, actually. It's because NADPH has got to come into the pores and then go back out again. You know, what you do instead is now have isocitrate coupling and pulling the cascade along, and you work out now what was your optimum concentration of NADP that you needed, and now it's actually about 20 micromolar. And this compares the currents under coupling. This is the red points, coupling to the cascade reaction. The current observed here compared to the current observed when you use no coupling as a function of the NADP concentration. And the difference is more than 100-fold. And in a way, this represents the proof that a nano-confined coupled system is orders of magnitude more efficient than were that solution not to be coupled and channeled. So very finally, we can use this to look at the action of a cancer drug. So this looks far removed now from making high-value chemicals, but it's an interesting idea. Isocitrate dehydrogenase catalyzes this reaction. Whoops. So it takes isocitrate to 2-oxoglutarate, and it's a reductive reaction. It releases CO2. There's a variant which occurs with isocitrate dehydrogenases, particularly at one near the active site, which completely changes that activity. And now the activity switches instead to the reduction of 2-oxoglutarate, reduction of this, to 2-hydroxyglutarate. And this occurs in patients with myeloid leukemia and brain tumours. They have this reaction. Basically, it's removing this central metabolite from cancer cells, which with quite devastating effects. And there's various drugs which have been developed, of which is only one which is clinically approved, to actually inhibit this oncogenic activity. And this drug I show here is ivosidenib. It's marketed by Agios Pharmaceuticals, and it binds at the interface of the two monomers on the IDH molecule. And we can look at that reaction, the inhibition of the enzyme using the electrochemical leaf. The important point is that the binding of the inhibitor is slow, and the binding as an inhibitor is extremely tight. It's of the order of nanomolar, tens of nanomolar amounts. And because it's slow and the binding affinity is so great, it's very difficult, in fact extremely difficult, to get any information about the kinetics of the reaction from conventional enzyme studies. This is an experiment in which we've loaded 2 isocitrate dehydrogenases into the pores of the electrode. One is the native enzyme which catalyzes the oxidation of isocitrate, and one is the variant which catalyzes the reduction of 2-oxoglutarate. And what we're doing here is we've set up the voltammetry. So we've got the green voltammetry here. This is oxidation of isocitrate by the native enzyme. This is the reduction of 2-oxoglutarate by by the variant enzyme. And as we add the inhibitor, what we're doing here is we're decreasing only one of the activities. So you can imagine that this is the voltammetry of a cancer patient's drug resistance and drug effect on an important enzyme. The inhibitor is affecting only one of the activities. It's only affecting the variant enzyme as the activity drops. And finally, you end up with a red voltammogram here. Well, out of all this, you can get a massive information because what this does, because you're looking at the rate of change of rate directly from plots such as this here, you're able to determine very accurately the dependencies of catalytic rate on the inhibitor concentration and so on. And one of the things that out of this, one of the things that you would notice, this is a plot of the rate of inhibition as a function of the drug concentration. You get an intercept here on the axis, and of course that's an equation of the form that K observed equals K on times inhibitor concentration plus K off. It's a reversible reaction. So you can find here the rate at which inhibitor comes off the enzyme. And finally, it enables you to build up this picture of how the enzyme actually works, which is not actually available to the drug company. They don't know, they can't determine this sort of information, and we're able to do it very easily. Anyway, so there's a lot of implications of this technology, because we, I can just pick out a few things here that I like buzzwords, and we turned enzyme cascades now into cascadetronics, because you can now use the use complex metabolic pathways and treat them now like electronics. And I think we've only just touched the tip of the iceberg, given the vast number of enzymes that we could now study. So I'll leave you with that, and finally, the small group. I'm proud of only having a small group. You know, there's a small number of people here have done a tremendous amount of work, and thank you very much for listening.
Great way to see the blending of biocatalysis, enzymology, and electrochemistry. So it's quite something of a great potential. I have a question before the rest of the people ask you. The enzymes, when it's in solution, it gets into the pores just by simple diffusion, but there's some driving force causing them to get in there.
No. So you've got two ways of doing it. You can either expose your modified electrode, which has got the ITO layer on it, expose it to the enzymes in dilute solution. Now, you can do it overnight if you want to do that, and then you just wash off the excess. Or what we prefer to do now is just basically to paint a solution on the top, and then half an hour later it's ready to use. The one of the important parameters, you've got a couple of things. What enzymes you put in, so it depends on what reaction you want to do. How much of each enzyme would you put in? Because a slow enzyme, well, if you've got a slow enzyme, you just use oh, louder, sorry, yeah, I was looking in the wrong direction, yeah. If you've got a slower enzyme, you just use twice as much of it. Your final limitation is how many enzymes you could pack in the pores. And so I gave an idea of that. You could pack possibly up to 5 millimolar FNR or 6 millimolar. When you get to the bigger enzymes, 1 millimolar or so on. So what we're investigating at the moment is ways of making the pores larger so that you can house more electrodes. It is quite intriguing why enzymes would go into the pores. They go in spontaneously. We're confident of that now. It looks like a wonderful case of entropy. They're working very well for you. Big molecules like pores.
Yeah.
That's it.
Well, thank you very much. Any question, please?
Thank you very much. A very nice talk. My question is more or less related with the question that the previous question. How do you study other semiconductors more than iridium tin oxide, and also about the porosity, to control the porosity?
These are quite doped. They're not really semiconductors. They'd be metallic. They'd be basically treated as metallic conductors.
It's not supported, or it's not mixed with the iridium tin oxide?
No, iridium tin oxide is a material which is basically treated as a metallic conductor, because you've got a conduction band which contains quite a large number of carriers.
Okay,
it's a material which is optically transparent as well. It's just that wonderful compromise between electrical conductivity and but that's not really relevant from our point of view. The important point is hydrophilic. It's a beautifully hydrophilic material. So you make nanoparticles and they fuse just like a pile of bricks, as I pointed out earlier. How you control pore size, use larger nanoparticles. That would be one way of doing it, which we haven't really gone and looked at systematically yet.
Okay.
Have you ever run try to run these for fuel cells?
I've sort of given up on fuel cells. I sort of fuel cells. I don't. Yeah, it would. I did. I actually published a thing on using a fuel cell, an alcohol fuel cell. Yeah, yeah. But it's not gonna make much difference to technology. I think the advantage here is that it's a way of controlling extremely complex behaviour, and it brings it all very easy, makes it all very easy to see. And either whether you're doing whether you're scaling up to do pharmaceuticals, because you could easily see you can make a drug in this way if you have the right combination of enzymes, and that's something I'm trying to sell. The other side is, oh yes, sorry. The other side is actually enzyme chemistry itself, because you get another idea. You get other ideas about enzymes, how enzymes work. Those inhibitor experiments, you couldn't do them in solution because the binding constant is very tight, so it's at the nanomolar range, and in order to get an activity from the enzyme, you'd need to be working with enzyme at nearly micromolar range. So you can't do classical kinetics any longer. But it doesn't matter now, because you've only got a tiny amount of enzyme compared to what you would have as a drug, total amount of drug in a solution. So you're actually enforcing pseudo first order conditions on it in an otherwise very unusual way. But the enzymes are, of course, very crowded. So we were interested to ask, did they behave any differently? So we did the best experiment possible to compare the binding of the inhibitor in dilute solution. And we were able to get so far. I should add that the inhibitor first of all binds to the enzyme quite tightly, but it doesn't inhibit it. And it's the inhibitory step that we actually get. And drug companies have measured the binding of the, as well as measuring the IC50 values, which they use, they measure the binding of the inhibitor by either surface plasmon resonance or non-denaturing mass spectrometry. But that just tells you that the inhibitor gets bound. It doesn't tell you, of course, that it's inhibited the reaction. And you don't see that. But in our case, you very easily see the second stage, which is where the inhibitor moves and locks into place at the dimer interface. So it's pretty subtle, but you get the detail that you don't otherwise see.
Thank you very much. A quick question. In your slides, you showed that the system is compatible with kinases and other enzymes.
I'm sorry, I can't. It's you. I can't hear now. I can't hear what you're saying.
Oh, on your slides,
yes,
you showed that the system is compatible with kinases and other kind of enzymes.
Yeah,
right?
yeah.
But in your work, have you found any enzyme that doesn't quite work?
Yeah, we've got one at the moment actually. So we're looking at formaldehyde metabolism, and it looks to me that the problem is that formaldehyde is a pretty nasty molecule to put in the pores because it starts to degrade the FNR. But we've never encountered that before. So that's what I'm thinking. There are going to be examples, I'm sure, where the system is not compatible. But my hunch is that it's going to be compatible for most soluble enzymes, not membrane-bound enzymes, but soluble enzymes.
I think that's it. Thank you very much again, Dr. Armstrong. Very nice work.
Now we're moving to our fourth talk of this half marathon so far. This is Professor Jenny Zhang from Irvine in California. Jenny's research interests include the discovery and study of inorganic electrocatalysts for the generation and utilization of chemical fuels. Current and prior research include oxygen activation, hydrogen production and oxidation, and carbon dioxide reduction. These studies have primarily focused on the effect of bio-inspired secondary coordination sphere interactions and the effect of thermochemical properties on catalytic activity. In her webpage, I also saw this thing that I really want to mention, particularly because we've been discussing this the whole world over, and particularly here at the chemistry school. What she has at his webpage is that in this lab, she says, we believe science is real, love is love, Black Lives Matter, feminism is for everyone, electrochemistry is cool, and immigrants are welcome. So please have Jenny. Welcome to Mexico.
Okay, thank you so much. I'm very excited to be here today. This is my second time to Mexico, and I always have a really good time. It's just a really beautiful country, and also just being on campus today is very exciting for me. As I'll mention at the end, one of my current postdocs got her PhD here. She tells me about it all the time. I hear about lots of different things, and now it's nice to see it in person and be here. So I'm going to talk to you today a little bit about electrochemical CO2 conversion, capture, and concentration, and possibly combining the two. I'm glad Alyssa went first because she introduced a lot of the topics that I'm going to talk about today, so I don't have to spend too much time on them and why they're important. I think many of us are aware that the CO2 levels are rising, and it's because we basically burn fossil fuels. We're digging, archaic carbon out of the ground that was fixed photosynthetically over millions of years, and we're basically all oxidizing it all at once, which is changing our atmosphere in negative ways. And we like to basically find ways to resolve this. And as Alyssa pointed out, we would like to close the carbon cycle, right? So right now, we dig fossil sources out of the ground, and we burn them, we release the CO2 without any thought of putting all this pollution into our atmosphere. But more ideally, closing that cycle, as she also pointed out, would basically be to capture CO2 from various sources, either from air or from point sources, and then utilize them in some cases. As she pointed out, we cannot decarbonize our economy. We use carbon in polymers and in lots of different materials. We can also use it as a way of storing energy in the form of fuels. But we would like to basically close that and recycle that back into utilization again. Or because we have already put so much into the ground, we actually have to go carbon negative now and sequester them. And you might think it's funny that I have, I don't know if they can change the aspect ratio on the, I'm a little cut off on the edges, but it might be funny that I have an oil well there for sequestration, but a lot of the best places right now to sequester CO2 is in formal oil wells. And in fact, actually also currently the best use of recovered and concentrated CO2 is an enhanced oil recovery, basically putting it down into wells in order to extract more oil. Okay, so I'll talk a little bit first about utilization, because that's where I started when I started my research program about 10 years ago, is we were really thinking about how do we functionalize CO2 and make useful products out of it. And we were very much inspired by the area of artificial photosynthesis, where plants utilize water and CO2 and sunlight to basically fix carbon into CC-CH bonds. And artificial photosynthesis is doing that exact same process, except using artificial means to do so. So we can use a photovoltaic to collect that light energy, separate to electron hole pairs, and then we can basically run very similar reactions that happen in nature, where on the anodic side we're oxidizing water into O2 and then using the protons and electrons to reduce CO2 into carbon-based fuels, or just take the protons and electrons directly into hydrogen, which is also a fuel. And then certain ones of these are a little bit more desirable because they're liquid fuels, like formate or any kind of hydrocarbon products have more value because they're in the form of liquids. And one of the biggest challenges that we have in this area of CO2 reduction and electrocatalytic CO2 functionalization is selectivity. How do we get among all these different products? And it seems at first that it shouldn't be that difficult of a problem. If we think about what we're doing here, we're taking CO2 protons and electrons and then putting them with a catalyst, right? There's only 3 ingredients. How many different products can you make? And we can actually make a lot, right? And these are obviously not the whole spectrum, but these are all things that are not uncommon products of electrolysis, just adding these 3 ingredients in. And one of the reasons why that selectivity is such a challenge is because the standard potentials for many of these products are very close to each other, right? So thermodynamically, they are all accessible at certain potentials, and so they're all basically available as products as we do reduction of CO2 under proto conditions. And the one that I think many people have focused on are the 2 electron products, which even by themselves, even though they're the simpler products, are still quite complex when it comes to selectivity. And those 2 electron products are 2 protons and electrons directly to H2. Whenever you do reduction of a product solution, it's very easy to evolve H2. It's a very mild potential. And then you can also get CO2 to formic acid, which is a 2 proton, 2 electron process. And you can get the 2 proton, 2 electron to CO in water as well. So when we think about doing catalyst design in order to understand how to get selectivity for CO2 reduction, I always see it as this. Catalysts have choices to make on who they want to react with at various stages in the catalytic cycle. For a lot of catalysts, there are intermediates that can favor either reacting with protons or CO2, and then depending on where that selectivity lies, which road they go down on at specific intermediates, it really dictates what the final product is going to be. These reaction diagrams get quite complex, but in the end, reaction product diagrams all come down to what order do these protons and electrons and CO2 react in order to get to different products. There are, of course, 2 different ways of accessing, controlling either proton or CO2 at a specific step in a catalytic cycle. One is thermodynamic control. One of the reactions is endergonic, delta G is positive, or one of them is exergonic, delta G is negative. And then the other way is kinetic control, right? So these are the sort of handles that we have in order to control reactivities at these branch points in catalytic cycles in order to dictate what the product selectivity will ultimately be. We specifically focused initially on protons to H2 and CO2 and protons to formate or formic acid. And the reason for that is that there's a very well understood intermediate that's involved in both of those catalytic cycles that we wanted to try to understand and control in order to get selectivity. So when we think about hydrogen evolution, which people have been studying hydrogen evolution in molecular inorganic catalysts for a couple of decades now, they almost all go through metal hydride intermediates, right? So the metal gets reduced, it gets protonated to make an MH bond, and then that MH gets protonated again to make H2. Alternatively, another reaction can happen is that metal hydride can transfer to CO2. So Fraser gave a nice introduction to hydride transfer in nature, very often nicotinamides. We often in synthetic inorganic chemistry think about using metal hydrides as our donors, like we often use aluminum hydrides and things like that. So metal hydrides can also donate and react with CO2 to make formate as well. And so that metal hydride is that really important intermediate that we really need to understand if we want to steer reactivity in one direction or another. And so one of the metrics that we can use to think about metal hydrides is this term called hydricity. So hydricity is a free energy, it literally is the heterolytic bond cleavage energy of MH to make M and H minus. But what it is, it's a measure of like the ionicity of that bond or how prone that MH is to giving up the H minus, the weakness of that bond or the strength of that bond. And so our question that we had was whether we can use this bond metric in order to tune selectivity for either protons or CO2. So what do we know about hydricity? I'm going to talk a little bit more about it because it's going to come up in this first part of the talk. So one, it's experimentally measurable, which is nice. I like to quantitate things and not necessarily only through DFT, but also through experimental measurement. Before we got started, many of these had already been measured, which is really valuable for us as a starting point. You can see here, these are metal hydrides that have been measured in acetonitrile and water. Let's see if I can point a little bit without. So one thing that you'll note is that the hydricity scale is on the y-axis. And the way that we read these scales is that as they go down in number, the bond is weaker, right? It's a weaker bond energy, so they're more prone to giving up their hydride. So things like borohydride, aluminum hydride have very low hydricity numbers. That bond is very weak. And then another thing you'll note is that because you can see these correlations with redox potential, they do correlate with redox potential, where compounds that are more reducing are better hydride donors, right? Which is sort of intuitively we would think that as well. If we want to reduce something, something that has a more negative potential would be more reactive in that sense. Just to show you a little bit about the tunability here, this in acetonitrile, we can basically span 30 kcals per mole in this bond strength, which is very valuable. And in this graph here, all of these orange triangles that span about 20 kcals per mole are all just nickel bisdiphosphenes, right? So we have a lot of ligands in our organometallic toolbox, but if we just pick one of them, diphosphenes, we can already tune these metal energies, metal hydride energies by 20 kcals, which is pretty tremendous. And then these other metals as well, you can see basically you can just, we know a lot and we understand a lot now about how to basically change metal ligand environments in order to get the exact number that we want or in the direction that we want as we tune. Okay, so I'm gonna talk a little bit through some of the thermodynamics of metal hydride reactivity. This is again our catalytic cycle for hydrogen evolution. And so we can describe this protonation to make hydrogen using a free energy equation. So the way that I think about this is that if you're making hydrogen in this step, you're breaking an MH bond and you're breaking an HB bond, right? Which in that HB bond will depend on the pKa of that acid. And then you're forming one bond, which is H2, and that's a constant. So the two factors that matter for the free energy of this protonation reaction are the hydricity and the pH, the two bonds that you're breaking. And then the one you're forming, H2, is that constant. So basically what I did was I drew these into these diagrams like this to sort of reflect the information that's in this equation. So on the y-axis, again, I have hydricity. Again, low hydricity means a better donor. And then here I have pH. And this black line represents when this delta G of protonation is 0. So this is like the black line in a Porbet diagram. It's basically ergo-neutral. And that if we have combinations in this region that's green, H2 evolution, that this reaction will be, delta G will be negative, right? It'll be exergonic. And if we're in this blue region, that means that delta G will be positive. So intuitively, hopefully this, if you think about it, it will make a little bit of sense. If I have a good hydride donor like sodium borohydride or sodium aluminum hydride, you probably know you shouldn't put it in water because it'll very quickly protonate, make H2, a lot of heat, might get a fire. We don't like fires in our lab. So you know, these very low donors, they are not stable at almost any pH, right? It doesn't take a very strong acid to make H2, whereas as we get to weaker donors, as we go up, you need a stronger acid to evolve H2. And under some conditions, there'll be such a weak hydride donor that they are actually indefinitely stable even at pH 0 because they just, that formation energy will be positive. So when we started working on this, a postdoc, Charlene, made this molecule. This is a nickel DHMPP. It's another bisphosphine, but one thing that's unique about it is it's in water. This scale is all in water. We wanted to work in aqueous solutions. And she measured the hydricity, and it was 30. And according to her hydricity measurement, that means that this should be a good hydrogen evolution catalyst below pH 3, because H2 evolution will be exergonic. And she, in fact, showed that. So one of the cool things about this molecule is that it was stable at 0.1 molar H2SO4, which a lot of organometallic compounds are not. When she does electrolysis, she gets very high ferritic efficiencies for H2 evolution, a fast catalytic rate, and it was a very stable catalyst even after 18 hours of electrolysis. So that was cool, but you know, at this moment in time, we were like, well, we know a lot of catalysts that are pretty good at making hydrogen, although this was a little bit unusual because they worked at pH 1. What we really want to do is actually suppress hydrogen evolution so we can reduce CO2. And I always tell my group that one of the reasons why we do hydrogen evolution is that when we want to do selective CO2 reduction, we need to make a bad hydrogen evolution catalyst. And knowing how to make a bad one is helpful when you know how to make good ones. So according to our diagram, this particular compound should not evolve H2 at pH 7. That reaction is uphill. And she did in fact do electrolysis at pH 7. And you see pre-electrolysis, she has the nickel 2 that she starts with. And then post-electrolysis, she basically gets 2 electrons reduced, protonation, and then it stops, right? Because that reaction is uphill. So she's able to very selectively generate a metal hydride reducing equivalent without co-evolving H2 with it, which is a really valuable discovery. And so then the next question is, well, now that we can very selectively generate these metal hydrides, can we add CO2 to them to get selective CO2 reduction to formate? So in order to understand that question, we go back to our hydricity measurements and how we can understand the thermodynamics of CO2 reactions with metal hydrides. So if we want to do this, it turns out that hydricity is actually also the key metric in determining whether CO2 will react with a metal hydride. So effectively, you could think about CO2 being a hydride acceptor or formate being a hydride donor. And basically what you want to do is you want to compare, basically which one is a better donor, formate or your metal hydride. If your metal hydride is a better donor than formate, then it will reduce CO2 to make formate. If it's not as good of a donor, then that reaction will be uphill to reduce CO2. One thing you'll note is that there's no pH in this equation. So there's no pH dependence on whether or not a hydride donor will react with CO2 to make formate. And so if we add that information to this diagram, the hydricity of formate or hydride donor ability is about 24 kcal per mole in water. That had already been measured. And so I can draw this straight line and say that metal hydrides with greater hydricities than that will not reduce CO2. It's uphill. And metal hydrides that are below that will reduce CO2 because it's downhill. And one of the cool things that we identified was that there's this triangle here of metal hydride combinations with pH where you can get selective reduction. So basically what I'm saying is that metal hydrides in this region under these conditions will be exergonic for making H2, but energonic, I'm sorry, they will be uphill for making H2, but downhill for making CO2 to formate. So you can basically get thermodynamic selectivity by operating in this region. So you might wonder a little bit if you do a lot of electrochemistry that I have possibly violated a law of thermodynamics, which we don't like to do in my group. And this actually bothered me because I saw this diagram that I just sort of reasoned out by looking at these equations. And in the beginning, I told you that the potential for CO2 to formate formic acid is negative of hydrogen. And so what that tells you is that there shouldn't be a region where you can get thermodynamic selectivity for formic acid, right? Because it's negative. But then I went back and looked at the Port-Bay diagram for CO2 and formic acid and water. And so, yes, indeed, at pH 0, standard conditions, this potential is negative of that of the H2 couple. And then, as you would expect, as it is a 2-proton, 2-electron reduction, that relationship follows a 60 millivolts per decade change by pH. But something very interesting happens at pH 3. And at pH 3, formic acid becomes formate. That's basically the pKa of formic acid. And so above pH 3, this is now a 2-electron, 1-proton reaction, and now this is a 30 millivolt per decade slope. And so essentially what happens is it crosses the H2 line, which is always 2-proton, 2-electron, here at pH 8, which is exactly where it crosses in our diagram as well. So everything is consistent in our diagram with thermodynamics, which is, like I said, we don't like to violate laws in our group. Basically what we've done is that by using these bond energies, we've redrawn a Port-Bay diagram. And I would argue that ours is more useful because it uses a metric that we can actually use to design catalysts, right? These metal H bond energies. But basically, it's all consistent with the Port-Bay relationships. Okay, so back to our story is, this catalyst that Charlene originally made has a hydricity of 30, definitely in the no CO2 reduction region, right? It's not a strong enough hydride donor. So then Bianca Ceballos, who was a graduate student in my group, made this nickel compound that's more hydritic. So basically she made it more electron donating. As I said, we understand how to change ligands to get the numbers that we want. And this one had a measure hydricity of 23 kcal per mole, which puts it in this region. So she was able to show that it could do hydride transfer to CO2, but it was extremely slow, like weeks. It was not going to be a good catalyst. And the reasoning that we had for that is basically at these pH values, CO2 is mostly bicarbonate and carbonate. And so there's not actually a lot of CO2 present under these conditions. And so to get around that, I said, Bianca, why don't we work on another solvent where we don't have to worry about these equilibria, just so that we could show that we can use these diagrams to design selective catalysts. And so Bianca picked this platinum catalyst that had the right hydricity. It had already been measured before to be about 41 kcal per mole. And by looking at our diagram that's been redrawn with all the thermodynamic constants in acetonitrile, this should be selective for CO2 reduction using a pKa acid with a pKa of 30. And she picked phenol for that purpose. So what she did was that she took this platinum system and she wanted to show that it can in fact evolve H2 under the wrong conditions. So she used a strong acid and showed that you get electrocatalytic H2 evolution. But we wanted to show that we could basically turn this off by using our thermodynamic scheme. And so here is our cyclical tammetry in black. you can see that it's a 2-electron couple for the platinum 2,0. So this black is just the native compound with no substrate present. If she adds 1 equivalent of phenol, we lose reversibility after reduction to platinum 0. And the reason for that is because it's protonating to make the metal hydride. So it's an EEC reaction. So we get 2-electron reduction, protonation, and then it stops, which is exactly what we want it to do, right? We want to turn off H2 evolution. And then, so the real question is, if we add CO2 now, will we be able to intercept this metal hydride we generate to do catalysis? And the answer to that was yes. So when she adds CO2, which is this red cyclic voltammogram, basically we get a catalytic current. And so essentially what we're able to do is basically turn this reaction on and then add CO2 in order to get selective reduction to formate. And in fact, the Faraday efficiency was greater than 90%. We don't detect any H2 present when we do catalysis, and it's fairly low over potential. So I really like this result partly because it was sort of a proof of principle that we can use thermodynamics to basically control reactivity at intermediates in order to get selectivity. The second reason why I liked it is because platinum is very well known for being a hydrogen evolution catalyst, and we were able to use thermodynamics to turn that off and basically make it a CO2 reduction catalyst instead, which we were pretty excited about. You might wonder, we thought a lot in the first couple of years of my group about using thermodynamics to basically steer selectivity. Of course, the other way to do that is through kinetics. We are working on that as well. I don't have as much to talk about that today, and I'm just going to go through one slide that shows some of the work we've done in this area. But a former student, Jeff Barlow, made these fairly complicated compounds with heterobimetallics. And one of the things that he noted about them is that when he adds sodium or barium into these crown cavities, you basically increase the overpotential for hydrogen evolution. So it's basically a way of kinetically inhibiting this reaction. And the way our hypothesis as to why this happens is that, protons are charged, CO2 is not. And so by putting a local charge near active sites, that we can basically, we hope, inhibit the approach of protons and basically increase that over potential for hydrogen evolution as well. And this is an active area that we're working in right now. So I talked to you a little bit about our work on CO2 utilization. Like I said, that was a big focus of my group in the first couple of years. But this sort of came up. I don't know if you guys have this expression with the elephant in the room, but basically, where does our CO2 come from? Well, we buy it, and it comes in a tank, and it's clean, and it's under pressure. But in real life, if we want to have CO2 utilization, we have to think about where this comes from. And Alyssa touched upon this as well. So the state-of-the-art carbon capture technology right now is just not very good, and I think some people mentioned that as well after Alyssa's talk. We can figure out what the minimum energy it is to concentrate CO2 from different sources just by using the second law, right? You probably all remember this from freshman chemistry, or maybe don't want to remember it, but anyway. You can use this equation, for your initial partial pressure all the way up to 100%, right? Standard conditions, and figure out what the thermodynamic minimum it is to concentrate CO2 from various sources. So from flue gas, which we'll just estimate at 10%, it's usually 5 to 15%. It's about 1.4 kcals per mole CO2. So that's actually a pretty small number for concentrating. That's the minimum energy. The state of the art, as Alyssa talked about, is the Petronova plant. There's another plant in Canada as well. There's basically 2 working plants for CO2 capture from flue gas. As she mentioned, they use these alkyl amines. They absorb CO2 in a 2-to-1 stoichiometry from flue gas concentrations, and then they're thermally heated to desorb. So these plants, as she pointed out, are very inefficient. The actual energy cost is about 45 kcals per mole. This is about 3% theoretical efficiency. And as she pointed out, they are able to use process heat from the fossil plant, which is a free energy for these capture plants, but they also have to burn about 30% more fossil fuel in order to capture from the first ton of fossil fuel that you burn. So they're not very, very effective. In fact, there's a very big debate among clean coal in the US and how clean coal is not really clean for this reason. If we think about air capture, 0.04%, it's a little bit more energy, right, to concentrate from that low percentage, about 4.5 kcals per mole, but it's still not very much, considering the energies that we often use. Climeworks, I did a little bit of homework on trying to figure out what the overall efficiency was. They use sorbent materials, and they're desorbed using reduced pressure and heat, so it's also a thermal cycle. but they're estimated to be about 150 kcals per mole. So we're again looking at about 3% theoretical efficiency. So basically, there's a lot of room for improvement in carbon capture and concentration, partly because of these thermal cycles. The technology that we have right now is not very good. And if we think about it in the context of utilization, we spent a lot of time trying to reduce overpotentials in my group. And Jeff, one of my students, did this calculation where he said, let's take this number, 45.5 kcals per mole, to get capture and concentration from flue gas, and let's look at a good catalyst for electrolysis. And so this is a number that Jaramillo provided to me, which is that a realistic electrolysis system would run at about 3 volts. We could do, again, some freshman chemistry, figure out how many kcals that is. And basically, the answer is that, if we take capture from our current flue gas technology to 100%, and then to CO, about 40% of the energy that's being used is just in the capture part, so there's a lot of room for improvement there. If we basically do the exact same calculation but use air now instead, like Climeworks type CO2, it's about 68%, because that's so inefficient of the energy used is just in the capture part. So this is why we're sort of motivated to start working on capture and concentration. A few years in my group, we've been doing it for about 3 or 4 years now. So as someone pointed out after Alyssa's talk, which I was very excited about as a nice lead-in, we work on electrochemical CO2 capture and concentration. And the reason for that is that the efficiency potential is just much higher. All thermal processes are going to be Carnot limited in efficiency. That's about 30%. In real life, when you use things like water, it's actually much lower because you can't get a large thermal swing. And on top of that, a lot of compounds that absorb CO2 don't like heat. They tend to decompose over time. Electrochemical work can theoretically get to 100%. Obviously, in a real system, you would never do that with all the other resistant costs. But basically, the ceiling is considerably higher for electrochemical capture and concentration. Obviously, we use low-cost renewable energy. It's becoming cheaper all the time, and most renewable sources come in the form of electricity. Most renewable energy comes in the form of electricity. You get low-temperature operation, and then high-pressure desorption. So compression is a real energy cost in current thermal cycles, but these should desorb at higher pressures. And then obviously they're more modular, which is a lot of the advantages that electrochemical processes typically have. Okay, so what does this look like? There are a couple ways you can do electrochemical capture and concentration. I'm just going to talk about one of them today. We have a couple different directions in my group. The one that we probably spent the most time on so far is using redox carriers. So this is what it looks like in my non-engineering brain. Basically, we have a molecule that exists in 2 different oxidation states, R and R minus, right? R minus has a very high binding affinity for CO2. So it captures in its reduced state. So you can put your mixed stream in, and the CO2 depleted stream comes out after it captures. Then this goes into the anodic chamber where it gets oxidized, and then in the R form, it has very little binding affinity for CO2. And so basically, this is where you get compression out and concentrated CO2. Then you can take R back into the cathodic chamber and then re-reduce it. R minus, send it back in to capture more CO2, and then repeat the cycle. So this is often called electro swing as opposed to a thermal swing cycle. One other way to think about it is like it's a CO2 pump operated with electricity and electrons. So we're not engineers, but we were really, really curious about these redox carriers, right? These chemical compounds that we use that are redox active that can capture in one state and release in another. So we sort of focus a little bit on that. I can talk about some of the criteria that we need. 2 reversible redox states is one of them. In one state, which is typically the reduced state, it captures CO2, very large K1 binding constant. And then upon oxidation, very low K2, so it will basically release the CO2 in that state. So those criteria: binds tightly when reduced, negligible affinity when oxidized. And then there's actually a third criteria that had really limited this field. So this field's been around for a couple decades, but one thing that was really a barrier to any kind of adaptation, including the electricity was more expensive, is deactivation. So if your carrier is, if your carrier is reduced and the potential is negative of the O2 minus couple, oxygen is very reactive, right? Oxygen wants to be reduced. And so what can happen is you can get one electron chemistry to form superoxide. Now you've mitigated your carrier, and now you have superoxide running around, oxidizing things in your system. So none of the systems that had been reported when we started doing this were stable to oxygen, and that's a real problem because there's no capture application for CO2 that doesn't have oxygen present. So that was one last criteria that we had, was that the redox potential had to be positive of the O2 superoxide couple so that we could basically mitigate this one electron reactivity. So if I draw those two criteria on a graph, if I assume that there's no affinity in the oxidized state, and that we are really concerned about K1, the binding affinity when it's activated, and its redox potential, basically I can draw my criteria on this graph. So if I want to capture from flue gas, K1 has to be about 10 to the 4 or higher. If I want to get from atmosphere, it has to be about 10 to the 6 or 10 to the 7 higher binding. Just the metrics of binding constant and potential, which we were not trying to optimize for, it's already 2 times better than alkylamine capture in terms of energy efficiency, which is a big plus. And then one of the things I always really like about this system is that it's very simple. It's just 2 commercially available compounds. My students don't like to do large organic syntheses. They don't like to run columns. So they're very happy when they can buy something and then use it, and test it in the lab and just add ethanol in order to get this type of behavior. So that was very exciting. So the question is, where do we go next? We are trying to better understand solvent electrolyte properties in general, electrolyte engineering, in order to steer the properties of quinones to where we want them to be. And then an interesting conversation has come up when we talk to people that work on this in industry in carbon capture, is that for them, a lot of flue gas is not, they don't really care about it because they get so much free process heat that using electricity to them, even if it's more overall efficient, is not necessarily a win for them. So we've been thinking a lot more about things like enclosed spaces, which, if you've been following CO2 levels during the pandemic, tend to go up when there's a lot of people in the room, which gives us a slight advantage for capture. And then there's sort of low-hanging fruit like cement biogas, which has very high concentrations of CO2 coming off, which of course makes it easier for us to capture because it's got a lower binding constant requirement. So our engineering collaborators have published a paper on sort of what are the requirements that are needed for these different conditions. So I'll just talk very, very briefly about a new project in our lab, just to sort of discuss it a little bit. Alyssa brought it up as well. One thing that you can think about is, instead of concentrating and then reducing CO2, is that you bypass the concentration step and you directly convert or directly react CO2 after in its sorbed form, right? So this is often called reactive capture of CO2. And the reason why that's really useful is that for almost all CO2 capture and concentration schemes, CO2 capture is passive, but it's the regeneration that causes energy, whether it's thermal or electrochemical, right? That's where your energy input is. And so if you can just skip that step, you can save a lot of energy in your conversion process. Just to give you a little bit more motivation for this, this analysis was done by the Department of Energy RPE program, where they basically showed that reactive capture, as opposed to a sequential capture, concentration, and conversion, could save you a lot of money in both energy use and in the capital equipment that you would need if you envision such a process. So we were very fortunate a couple months ago to be funded to run a center from the Department of Energy on reactive capture. The idea is that you can take CO2 from various sources, various dilutions, various contaminant streams, capture them. So we are investigating new classes of capture agents, and then directly reduce these at electrodes upon capture, and basically utilize them. And there's a lot of really interesting open questions too scientifically, as Alyssa pointed out. These communities often don't talk to each other, catalysis and capture. So trying to get everyone in the same room is a very good way to basically move that field forward as well. I wanted to acknowledge my group, who has worked very hard on a lot of different projects in our lab. The people in red are the people who worked on things that I've talked about today. The first part was funded by the Department of Energy. The second part on capture was funded by the Sloan Foundation. My postdoc, Anna, I didn't get to talk about her work today on bio-inspired metal compounds, but she is an alumni from here. And I also wanted to point out that there is a large program in UC to enhance collaborations with Mexican universities. I'm currently working on a proposal with a professor here at UNAM on this, but there basically are funding sources for both collaboration, for student exchanges. They used to have a postdoc program, which is not active right now, but hopefully they'll get that going again. But there's a lot of different, obviously, opportunities here, I think, for better collaboration. We all face a lot of the same problems in science, and energy, environment, and security, and all these things. And so it'd be great if we could have more conversations about this. But you can go to the website and learn more about this program. Thank you.
Hi, Jenny.
Hi.
Ivan.
Hi.
Nice to meet you in person.
Yes, very much so.
Very nice talk. It seems like the recurring theme is how to make something more nucleophilic rather than basic once you reduce it, right?
Yeah.
And so in the capture part, I don't know if I missed it, but it seems like you need everything to be dry. Because, I mean, you mentioned the alcohols, and then I assume that you have either no water or very little water present, so that you have you don't have that as a potential H donor, right?
So the tetrachloroquinone does not protonate with water because it's not very basic, but it does other reactions with water, which we're trying to design new quinones that won't have that problem. Another thing that we've seen is that when we use things that are more basic, sometimes when we generate the active species, they actually just deprotonate water, and then you get hydroxide. And actually, that is okay because hydroxide will also capture CO2. And so our other project on this is basically called a pH swing, which are basically molecules that instead of reacting directly with CO2 will change the pH of the solution depending on oxidation state, and then we can use that as a way of capturing and releasing. Yeah.
And so just to finish this, so the input gas that you have has to be somewhat dry then. Is that the case?
We would very much like so the desirable thing about pH swing is that because you're in water, it doesn't matter.
Okay.
So I like that, and that's why we've started putting more emphasis on that in my group instead of the carrier agents. Yeah, but
thanks.
Yep. But it's an important point because especially flue gas is very humid and other sources are very humid.
That's beautiful stuff, Jenny. How do you, what's the ways that you can further tune your system or optimize it with consideration of mass transport? So you basically you were showing Paul Bay, you were showing sort of Paul Baydine, which are equilibrium potentials, but of course if you flow something, you can you can actually twist that around a bit, can't you? It's particularly if you've got when you've got small amounts of material, which of course are dissipated, you really have a large change in the thermodynamics. Because of course, we always think of reduction potentials, but of course, reduction potential is it's usually defined as a certain equilibrium state.
Yeah.
And of course, in electrochemistry, kinetics, you can upset that considerably with mass transport tricks.
Yes, I agree with that. It's interesting in some of the more, I guess, heterogeneous electrochemistry where they look at you're basically getting proton depletion at the electrode, right? And so you have a more alkaline environment that you would expect based on the bulk solution. Is that what you're talking about?
What about flow, putting a rapid flow without putting up your cost, I suppose?
Well, I don't know about the catalysis part, but for when it comes to the electrochemical capture concentration, so like I said, we work with engineering collaborators, and obviously in our lab we do everything as a batch, but they are trying to design cells because they think ultimately anything that captures and releases will be in a flow, because that's the only way you can get a lot of electrons transported, basically. And right, because I mean our cycle is 1.5 cycles because it takes 6 hours each cycle, But if you did flow, you could actually get a lot more contact area and move things a lot faster. Yeah.
Hi, Jenny.
Hi.
I'm Kobe.
Hi.
Hi. Nice to meet you in person as well.
Yes.
I'm just curious about your nickel hydride compound, the
Yeah.
one that you did with the OH hanging around.
Yeah.
You did that to make it more soluble in water?
Yeah, yeah.
Because the regular DP is, the nickel hydride is soluble in water.
Some of them are. I don't know.
No,
I guess
they are,
The
indeed.
DPPBs. Well, I guess we
Yeah.
never tried them. I guess we felt like we needed to.
I wonder.
Yeah. Oh, interesting.
Yeah, because we had the NMR in
Oh.
filtrated water.
Well, that's like.
And that's soluble and
Yeah.
that's stable.
I guess my conventional wisdom failed me. I just assumed it wouldn't be, so I
Yeah.
never tried.
Yeah.
Yeah.
Okay.
Okay.
Just a final thing.
Uh-huh.
How it compares the reactivity between nickel and platinum? You did the comparison?
Yeah, so nickel tends to be less hydritic. So one thing so nickel only works in water because hydricities drop in water because it stabilizes the H minus.
Yeah.
And so those values all come down by about 15 kcals. And so at least right now with using phosphine ligands, only nickel will reduce CO2 in water.
Okay.
They will not in acetonitrile, and that's why we go to platinum because we gotta increase the or
Okay.
drop the hydricity further.
Sure.
Yeah. Because they're more ionic.
Hi, Jenny. Thanks for the great talk. So I have a question about, like, there's this diagram where you have the binding constant and your redox potential, and you're trying, I guess the goal is sort of to reach the top right of the diagram.
Yeah.
So I'm a computational chemist, and when I see a diagram like that, I'm like, this is a great space for,
Yeah.
Using computational methods and high throughput virtual screening.
Yeah.
So I was wondering if there have been any efforts in terms of trying to computationally map out the space of redox active compounds to go towards that direction.
Yes. So we work with a computational chemist, Anastasia Alexandrova at UCLA. And this is not to say that, I mean, we should do it again, but like her postdoc during the pandemic calculated like 80,000 quinones for these properties and tried to correlate their molecular orbital diagrams, gave us, a dozen that should break these scaling relationships. We went through the trouble of synthesizing most of those, and none of them broke the scaling relationship. Some of them were actually worse. And our best conclusion on that, we did publish this last year, is that the postdoc who did the calculations did them all in the gas phase and didn't incorporate solvent. And the reason, actually, no, that's not true. He didn't do it in the gas phase. He used a dielectric constant. And our best hypothesis is that when we measure binding constants and redox potentials in acetonitrile versus DMF, the dielectric is basically the same, but we get very different numbers. So clearly there are like explicit solvent interactions that were not captured by the calculation. So I guess the moral is that you can't do it simply, that it's more complicated, but it's not that it can't be done. Yeah.
Is there any other question? No? Okay, thank you very much, Jenny. We will have a brief break until our next conference, which will start, I guess, at 1:15 instead of 1:30. Okay, so we will have just a brief break. Hold to your seats, but go out also and get something. There may be something to eat. Thank you.
but I grew up in Mexico City. And the first contact with chemistry was the International Chemistry Olympiad. You can see there Professor Gabriel Merino, which was part of our program. He's now in Simestar, Merida. And other people like David Maldonado and Carol Perelman. So that was when I was in the International Chemistry Olympiads. I'm this guy in the back with a mustache. Then I was here studying theoretical chemistry at UNAM. This is a picture back when we were doing theoretical chemistry in Química Teórica here at UNAM. Professor Enrique Hernandez Lemus is now a very famous bioinformatics person. That's how he looked when he was young. And I like to touch his belly like if he was like a Buddha. Then my undergraduate advisor was Professor Carlos Amador, and this is a photo that I have from him from about 12 years ago. Him and I, when I was already a professor at Harvard. I got my PhD with Professor Bill Lester at Berkeley. This is a picture of the group. Around the time I was there, I'm not there in that photo, I just had left. But I like his stance that people do science, so he taught me that people first, science second, and money third. So that's the most important thing, is take care about your graduate students and your postdocs, and your undergrads, and then everything will flow. That's the most important thing, being a person first and not ruthless. Then my postdoctoral advisor is Professor Martin Head-Gordon, seen there in the slides. And throughout the years, my lab has had a lot of Mexicans, Latin Americans in the lab. For example, you see there in this one, Joel Yuen Xu, even though his name is Chinese, Joel is Mexican. He's now a very successful tenured professor at the University of California, San Diego. Fantastic theoretician, you could also go work with him. And he himself has hosted many Mexicans in his lab already for all sorts of stages, visitors, postdocs. Some of his postdocs already are professors in Mexico, so they will be my academic grandchildren, Carlos Amador's academic great-grandchildren. So the gift keeps on giving. This is Adrian Hinich, which I am sure he will be a professor next year, given all the offers he has already. He's an incredible Mexican scientist that works in disease. He was one of my graduate students. And then I founded a quantum computing company called Zapata Computing, just to tell you also you can also do businesses. So hopefully you appreciate the name, but this is one of the largest quantum computing software companies. One of my co-founders was Latin American Jonathan Romero, sitting there very, very sternly with his pink shirt. So he's Colombian. Then I co-founded another chemical company called Keborex. When Trump was elected, I left the United States for obvious reasons. And then I moved to Canada, where I started my work on self-driving laboratories, which I'm going to talk to you about. Okay? So let's just begin with the team that made this possible. This talk is going to be about our work on batteries, which I have spoken here at UNAM before about my work on batteries. And this work started when I was still at Harvard with Professors Mike Assis and Roy Gordon. And you see kind of one of our early pictures before I grew a beard again with one of our flow batteries. I'll be telling you what they are. But also, what is really cool about this one is that we have a collaboration and parallel developments with UNAM here in Facultad de Química. There's a lot of research, as well as in INEL, on flow batteries based on this initial interaction. So this is an example where an interaction with, in that case, the United States and then Canada, creates kind of opportunities for doing programs that are in collaboration or parallel. And another success of this program is that in my lab, Professor Marta Flores, which I saw earlier, where are you, Marta? You just gave me a connector, thank you for saving me. Professor Marta Flores and Professor Andres Aguilar, which I mentioned before, raise your hand. Both of them were in my lab and they both became professors here. One is a theoretician, one is an experimentalist, and we work together on batteries. And Carlos leads the local project on batteries. Okay, so this is a collaboration that ended up being, interacting with Mexico. Now, when I moved to Toronto, we started with other projects, and the batteries was a little bit of a smaller project where it's growing harder and harder. Here are the people that currently are working on the flow batteries. Zhang and Han are leading it with very strong contributions from Felix, Shertian, Marta, and Tatsuya Simus, was by Simus. And now it's very important for Shertian to raise his hand over there. He's my graduate student, he's from Singapore, he's a rock star, so feel free to talk to Shertian. He did a lot of the computational work for this project. But I'm gonna start first with what's the whole point of what we're trying to achieve in a large Canadian initiative that we're working on. And it was already alluded by in the beautiful talk by Professor Chibuese. He was really showing a circle of what we like to call closing the loop, which basically means accelerated molecular discovery, accelerated materials discovery, using artificial intelligence to drive automated laboratories to try to accelerate the process of discovery, and I'll be telling you about that today. Okay? In other words, you want to think about it also as the make, design, test, analyze cycle, as the people in pharma like to talk about it. How can we, as quickly as possible, make materials to try to solve a problem? So in the very first few slides, I'll tell you an example of what I'm going to be talking tomorrow at Instituto de Química, because I know not everybody will go to 2 talks. I don't expect you. So I just want to show you what I've been doing, and then in lasers, and then I will expand on it on Instituto de Química. So the whole story is very long, but the story is the following. You hear about it tomorrow. If you have a cell phone, how many of you have a cell phone? Raise your hand if you have a cell phone. You've been burning your retinas with organic compounds that emit light at you. Okay? That's basically what you do every night when you cannot sleep and you're checking Instagram, right? So one of the interesting things is, what if you were able to do that with your glasses as you're walking around? The glasses sending signals to you. So I could imagine having all my chats in my glasses as I'm walking around. That sounds very crazy, but to enable that, you need to have directed light. It cannot be indirected light. It will be too diffuse. So for that, you will need an organic compound that emits lights straight at you. And that's an organic laser. So I'll talk to you more about them tomorrow. Here is the information. If anybody wants to take a photo of that or whatever, that's the information where the talk is going to be. But let's talk about batteries, right? I mean, the issue with batteries is that we keep going business as usual, growing the world population, and also, of course, developing. I mean, it's our right as developing countries to actually start using more energy per person, because wealth is correlated with energy. The more energy you use, usually, the better off you are. Think about Elon Musk. It's dramatic how this guy flies from one place to the Bay Area to the other in an airplane. I just can imagine how much CO2 you emit if you're rich, and how little you emit if you're poor. Right? So just for development reasons, we need to produce more energy, of course give it to the people that need it the most. But the other problem that we have is obviously, as it was already mentioned before by Eva, when energy is produced, renewable energy is produced, it's not necessarily when you need to use it. Okay? So you need to be able to store energy. And storing energy at the global scale is something that the humans don't know what to do yet. I mean, we know that we have technologies, we have not scaled these technologies to the level that we require. Okay? And you can see there the grid-scale storage power in gigawatts. It's a strange unit. You might need to be gigawatt hours. But even if it's in gigawatts, just look at the dramatic difference. So how much we can produce and less we can store. Okay? So we are working on a field of aqueous redox flow batteries. Okay, so what exactly is a redox flow battery as opposed to a regular battery? If you see here, you're going to separate the electrochemistry modules from tanks where you actually store solutions that are called negolite and pozolite. That basically, as they are pumped by these pumps into these electrode and membrane stacks, then you will be able to actually take electrons from one side of the battery and move them into the other side of the battery to create a potential difference, and then you can use to extract energy when you want to. So that's the principle of a battery. It's very cool because if the battery, if you want to store more energy, you make a bigger tank. Storing water is something that we know what to do. So water is the desired solvent. Again, Chibuese was telling us about beautiful electrochemistry that can happen without water. But if you don't use water in a flow battery, you have the problem that the solvent is quite expensive, and also it could be flammable and toxic, and other problems like that. So we're stuck with water in that sense, at least I think, in the flow battery. So this started actually, literally, I would say 10 years ago, when we reported the first organic flow battery, actually. So we started the field. This is usually not, you cannot brag about it many times, but we literally started this field 10 years ago with Mike, Roy, and myself, again, when I was at Harvard. That's a picture of our organic flow battery that uses quinones, that molecule anthraquinone disulfonate, has sulfonate groups to be solubilized, and uses a 2-proton, 2-electron process to reduce and oxidize back and forth. And in that case, we were using, as a higher potential pair, we were using bromine, and therefore we call it metal-free. But now, of course, as I will show you, there are many organic molecules you can use in that side of the battery. And this is a picture when I was pretending to be an experimentalist. Turns out now, 10 years later, we do experiments in my lab, as I'll show you. So I like this plot that I was looking at my old slides from 10 years ago. Just this morning, I was putting together this talk. And I found this slide that I had forgotten I had until now, this morning, which tells you, I mean, for the students in the audience, the simplicity of Hammett parameters, for example. This is different types of quinones, anthraquinone all the way with different substitutions, for example, and all the different groups, and how the groups either they raise the electrochemical potential or lower the electrochemical potential according to our calculations. The cool thing about quinones is that you can get a 0.1 volt error in prediction based on the simplicity of the molecule. So therefore, we were able to help the design of these molecules. But I also wanted to show you this 10 years ago our thinking, because it's going to change a lot with our thinking of now. Okay, so these slides that I just resurrected, we're thinking in the process of screening and filtering. Okay, so we had this molecular space shuttle database that allows you to actually store and plot different properties of molecules. And this is an example of what we like to call the baseball cards that we had. Actually, I say we had because this software is not in my lab anymore. We use different software now, use AI and other tools. We can see here the reduced and oxidized version of a quinone, the redox potential, and a bunch of other properties. And at the time, we calculated up to 1 million quinone molecules to kind of show the potentials of that class and then think about what will we do next, okay? So we also built graphs of the reduction and oxidation. If you have many OH groups, you can imagine that several OH groups can be reduced and oxidized in different ways. So you have to actually look at the entire redox network of all the quinones. So for those million quinones, we actually computed all of the redox network, okay? So that was a very exciting thing. So what did we learn? We learned that you have to work with experimentalists to try to think about what are the pathways that you need to actually block. For example, gem diol formation or Michael addition are very, very, very bad pathways that you actually had to avoid. Michael addition means the water attacks the electron-rich rings, and diol formation is just an equilibrium process where you form a diol and therefore slow down the electrochemistry. It's reversible, obviously you have to pay kinetically to bring it back, right? So it sucks. So we started making these plots where we looked at, for example, the hydration constant that we can calculate theoretically versus the redox potential and try to map about 1 million quinones. And these are the types of plots that we actually are able to find. We also are able to have Michael addition energies, and we want to have I forget, that's what I'm trying to learn from 10 years ago. Yeah, the larger the delta E of the Michael addition is better, so you want to be as high as possible in this plot, and as low as possible in the back plot. So you need to actually, as Chihuese was showing us beautifully, you have to actually look at two competing effects. One, that you have to be larger in one size and one in the other, and therefore, as you start doing that, you start screening and finding that there are less and less and less and less redox couples that could be good quinone flow batteries. Because you also want to think about, for example, not having more than 2 substitutions, okay? Also, they have to be very soluble. So after you look at that 1 million potential compounds and start screening, then you end up with hundreds or so of possibly synthesizable molecules, okay? And these are, for example, some of the visualizations that were very important at the time to look at the constants and the energies related to these. We were using these plots that are used mostly by people that do consulting, like in McKinsey. The bluer the circle, the better. So this tells you that the potential for the low potential or the high potential is not so good for these molecules, but they're predicted to have good hydration constants, which tells you that basically means that they're not going to form diols and then Michael addition energies. That means this might be prone to Michael addition. This one might, this might be prone to Michael addition, whereas this one might not be prone. This one even better. So it gives you a visual idea of which molecules you want to make and synthesize. Okay? Sorry, I am confusing myself with this project, with this clicker. So The problem is that quinones perhaps were not the most important class. There are quinones that have been made stable by the group of Roy Gordon and Mike Assis and even commercialized. A comment about commercialization that is really nice. We had the original patent on quinones. Mike and Roy just made a startup. And then before I was finding about the startup, I got a mysterious check from Harvard, which was from the patent. It was a very nice check, by the way, from the license, from the patent from Harvard to the startup. So commercializing your science sometimes can allow you to buy new, nice things, okay? So like my running watch or something like that. But you can see here our later work, which I really just want to tell you about. It's also quite old already, maybe 8 years old, when we actually went to molecules like aloxacins, which are basically vitamin compounds, like vitamin B12 derivatives. So you could also imagine having redox batteries made of vitamin B12 derivatives. And you can just imagine that this is just the tip of the iceberg. Chemical space is huge, so there's many more compounds that you can imagine doing chemistry with. So there is this review paper from my former postdoc. Oh my God, I think it got messed up a little bit with the fonts. Danny Tabor, he wrote this little paper in Nature Energy, talking about the potential versus the standard hydrogen electrode as a function of pH. So obviously you see that those kinds of plots that we learned here in Química Analítica 1, Química Analítica 2 and 3, you know, of pH versus redox potential, right? And in those plots that you thought they were going to be useful when you studied it and you become a professor at Harvard and now you remember Analítica 1 and Analítica 2 and stuff like that. Happens to me all the time, by the way. I think Professor Stivalet here taught me Michael addition. I had forgotten completely about it, and then I had to remember again about it. So anyway, that tells you kind of the compounds that are in the pozolite region that is important to find. So, okay. So where are we right now? What is the state of the art as of, say, 5 years ago to now or so? Okay, so what people have found in the recent era of the flow batteries, I would say the second most sophisticated era of the organic flow batteries, is that you want to have charged compounds so you don't mess up crossing the membrane. In the early days at Harvard, we had a lot of problems with our quinones crossing to the other side of the membrane and making a mess on the side of the membrane that you don't want to be. Whereas if you have charged compounds, and maybe you can also charge your membrane, like for example, you make it an anionic membrane, then obviously the positive compounds with the positive tails will actually be repelled electrostatically from the membrane, and therefore you prevent the crossing of the compounds from the membrane. So membrane engineering is also a big problem. Now, turns out that for the high potential, since then, a molecule such as this modified bitmap ferrocene, so this organometallic complex that we also learned in an inorganic class, turns out to be one of the best pozolites that we know. And this paper by Eugene Be, now the CEO, I don't know what's happening here, now the CEO of Kino Energy, the company I told you about, kind of started flow batteries that are potentially commercializable like this, okay? So you can see this bitmap molecule, obviously it's not a quinone anymore, but that particular molecule is an example of using these positively charged conjugated nitrogen groups to actually induce the right redox potential, but also induce the right solubility, more charges, the more soluble, and also repulsion from the membrane. Now, obviously, something that sucks about water batteries is that the voltage, by definition, is very small because you have the redox potential window of water. You don't want to be evolving hydrogen or oxygen. So you have to have a battery that is actually in between that window, and therefore, the voltages are usually 0.75 volts, 0.8 volts, things of that sort, the reported voltages. You don't really care too much about the reported voltages. You care more about the number of cycles that you can do. Capacity retention of this battery by Eugene is about 99.9989% per cycle, right? That's really amazing. That means there's very little degradation, right? So if you want to think about a battery, you really want to have a lot of cycles. And how many cycles does it make sense? Well, it depends what you're thinking about. But imagine that, as I like to say when I'm in Mexico, imagine a tinaco on the top of your house, like a big water tank, okay? And that's where you're putting your quinones. And like in Mexico, also el señor del gas, right? The gas guy comes in and fills your gas, you know, with a hose, right? You don't want it to happen every day, but maybe you want to change the quinone maybe every few years. So therefore, you want to have hundreds of charge cycles, thousands or tens of thousands. And this is an example of a battery that actually looks pretty good. The team has better batteries, but that's an example. So now I want to move on, and I'm checking my calendar, my time here. I want to move on to what we are doing in Toronto. So since I moved to Toronto, we started to emphasize more avoiding the screening approach and moving directly to active learning approaches. What does that mean? So screening is something like, okay, I'm going to actually generate a database of a potential big molecular family. I'm going to compute on it, and then I'm going to come up with some top candidates. I'm going to show them to an organic chemist and then pray and cry, right? Because the organic chemist will tell me this is too hard to synthesize. Or they will try it and the molecule will, degrade or something. So we needed to make the molecules faster, and that's when we started thinking about how to robotize this. How can we start thinking about synthesis procedures that are going to be able to be automated? And this is where Andres came into my lab. Actually, Andres started building the robots in Toronto. Actually, we sent him one back to collaborate with, so there's a robot in his lab, like the ones he built in Toronto, and we keep interacting. He's coming later, and we're working together. So he was tasked as a postdoc to figure out what would be interesting molecular families, and this is where Marta and her previous work with Carlos Amador comes in. We took a derivative of a family of compounds that Carlos and Marta were thinking about and told Andres, work with this master student Liam and make it happen. So Andres started learning about the chemistry all in the hood, where we started to think about what to do with it, all by hand. That was kind of like traditional organic chemistry at the time. But our big vision was to use a machine that was able to make this thing, also automate the electrochemistry, and then build a data set and continue. A data set of these new compounds that we didn't have, okay? And then, of course, we want to scale up, maybe with collaborations, and then get a paper, IP, etc. Right? So, what our main contribution to the project at Harvard, as I showed you before, is in this chemical science paper, where we explore the family of compounds that do redox chemistry, but we don't have enough high-quality experimental data to calibrate, because the way this worked is we had calibration to the experimental quinones. When this molecular class, we cannot calibrate it. So we need to actually generate the data with a robot to calibrate our computations, right? So Suleiman Air was actually a postdoc in my lab at the time, and he just released last year in Scientific Data his higher quality quinone database. So he has very expensive calculations on 31,000 molecules, basically quinones and as aromatics. So this is the state of the art now of quinone databases, but again, there's no databases for a molecular class. So, okay, so what do we do in our group? We actually have a paper by former undergraduate from my group, Akshat Nigam. This is perhaps the most productive undergraduate has ever been in my lab. I think he published 15 papers, I don't know. He was publishing like crazy since he was like a first-year student. And Akshat is now a graduate student in Stanford. So a lot of kudos to Akshat, that together with my postdoc Rob Police generated this genetic algorithm called Janus that uses a technique that is similar to parallel tempering in simulations, generates some compounds that explore. They're genetically optimized to explore, and some compounds that are genetically optimized to exploit. And you have actually population exchange between the two to actually computationally mutate molecules, and then based on fitness functions that were actually developed by Marta and Luis Martin, another Mexican in my lab, we are able to actually very quickly use genetic algorithms to figure out which molecules could be good molecules. So that's kind of where we want to get to, right? And we're doing some of that already with Shertian here, actually. Shertian is involved in that, in those type of calculations. So obviously what we want to do is do a data set that actually allows us to understand not only the redox potential, as we discussed, but now, because we're going to have an experimental setup, we're going to be able to, of course, look at what Diego was asking Eva just in the last talk in the other room. Diego was asking Eva about the kinetics of mass transfer, for example, right? Or passivation effects, or things like that. If you have a high throughput system, you should be able to actually, based on the description of the dogs, as Eva was calling them, in Mexico, by the way, Eva, we call them patitos, you understand a lot by looking at them with, for example, machine learning. So this is an example of the different methods and performance metrics for redox flow batteries, okay? So you need to think about, Coulombic efficiency, obviously, what is going to be the total energy density of the system, which obviously has to do with the solubility, for example, how many electrons per molecule you're actually storing there, right? You're actually, imagine that you could imagine having molecules that store many electrons, but obviously then they might be large and they might become viscous. So the molecule also doesn't have to be viscous. It has to be stable, and etc. There's also the redox potential has to be the right window, as I've been mentioning many times, etc., etc., etc. Information about the electrodes. So the very good news about this type of metrics is that we know what to go against. So now, this is the machine that I think Andres learned how to love and hate. I'll talk more about it in Instituto de Química. This is our ChemSpeed synthesizer that actually can carry out several parallel chemical reactions at once. We mostly have been using it for Suzuki reactions, but now we can use it for other reactions related to this mysterious molecular class. I won't tell you what the molecular class is during this entire talk, because we're in the process of patenting it. So I'll tell you everything, but what molecule is it? Okay? I'll show you its results, but you will have to wait until we submit the patent, which your name is going to be on it, Andres. So hopefully you get a check one day. Then you see over there the identification step, which is an HPLC, and the laser system. Again, tomorrow I'll tell you more, but what is really cool about it is that we have these little wires that can take whatever comes out of the synthesizer to the HPLC to do semi-prep separation, and then to our laser systems. So it's kind of like having, as I like to say, an organic chemistry lab, an analytical chemistry lab, and a physical chemistry lab run by a theoretician. Okay? So imagine the madness of that. Okay? But at least the order of the hierarchical order is actually there. I'm just kidding, I'm joking, with Professor Steve Allet. Now we want to do the same kind of thing, but for electrochemistry, and what you see there on the right is our electrochemical setup that, as you can see, we have been evolving in our electrochemistry work. Actually, Marta was the pioneer when she started working on this in the lab. And then since then, there was Samaila that left the lab too, and now it's Yang, which kind of took over the work from both of you. Okay, and Yang started building that little electrochemical setup over there. Okay, so I'm going to show it to you in a second, with the purpose of automating it. So we have, of course, gases that are there, like argon, so for example, to remove oxygen. We have a standard 3 electrode setup in these very, very simple vials. And we have pumps, we have pumps that actually transfer the liquids. So they're not shown here, but we can actually automatically, by these pumps, transfer liquids and transfer solvent. So we computer control the pumps with Python, and then we can actually carry out a static cell experiment. And then we can also remove the solvent from experiment, wash the cell, and continue. Okay? So it's simple, reproducible, inexpensive. You can actually do it here in Mexico with not too much work. If you want to send somebody to my lab, we can teach you how to build this thing with quite inexpensive pumps and things like that. Actually, you can see the pump there. Actually, you will see later. Tell me what this thing looks like. Think about what this thing looks like, and then I'll tell you what my postdocs came up with. Okay, but we're going to name our system after that pump that you see over there. Okay. So obviously, the reason that pump is called that inspired this Mario character called Toad, right, with the white and the red. So we call this thing eToad. Okay, and it has a software workflow manager, sorry you cannot see here very well. The hardware controller for all the potentiostats and the sampling systems, okay, and then a data manager that stores everything in our database. So this is the software piece, right, that kind of is equivalent to our previous molecular space shuttle, but for this particular system. So what has happened in my lab since 10 years from now ago is that we were all computational, and now in my lab, pretty much all the time, we have these hardware control layers. Because what we really think now is that chemistry has to be done in hardware and in computation in tandem. And that they all are the same thing, and that a theoretician and an experimentalist is basically the same thing. Okay, so for example, what are our workflows? For example, you can calibrate with eToad. You take, for example, iron hexacyanide, do square wave voltammetry, and then cyclic voltammetry. So with square wave, you find where the peak is. Once you know what it is, then you can go around it and do a typical cyclic voltammetry. We just got a tutorial about it in Eva's talk. And then, now I don't know what this is. Well, You can see on that screen, I don't know what happened here. Okay, and then obviously, what we want to do is, as our synthesizer, and I guess the projection guys just went for lunch or something, so I don't see anybody up there, so hopefully this works, okay? But if not, please look on the right-hand side and squint at it, right? So what we have here is the peak finding part, then the diagnostics, and there is where we can, for example, vary the scan rate, and as you know very well, that will tell us information about the diffusion, control processes, and the electron transfer rates. So now you can actually start doing some more diagnostic electrochemistry. And once we have this diagnostic electrochemistry and we can get the rates, then you start scanning many times and seeing if the molecule is stable. If you scan many, many times and the molecule doesn't degrade, gives you an indication that it might be a good molecule for a battery. Obviously, if you start scanning 3 times and the molecule degrades, there's some process that actually is degrading it and you might not want to use it for a battery. So this is a very good high throughput way of finding out if a molecule is good for a battery or not. Now, my lab is so full of stuff, literally physically, it's only one room. So now we're building a way larger space for robots in the University of Toronto, but at the moment there's a single room. So I told Zhang, the only space you have is one single cart. So he built a system where we have in one floor, in the parking, we have the solutions inside of this thing. By the way, this is a copy. This is for a copy machine, I think, or for a projector. So we have inside of it our solvents. In the first floor, we have a quite expensive, but we'll come back to it, biologics, 2-channel system. And in the top, we have all our electrochemistry gizmos. And we can move it around if we want to put it next to the HPLC, or we want to put it next to the synthesizer. It's kind of like a little... So everything that I've been told you today, all the data I'll show you, has been captured in that little copy card. Okay? So don't complain about not having space, just do what you can with the space you have. Okay, so now this is in the first floor we have this catholith and nanolite mixed, like this is the first generation. And then also with our 3D printer and with some commercial parts, then we also built a flow cell, which allows us to actually have less problems with electrodes and scan in a similar way as a flow battery. And we also purchased a little flow battery for testing. Okay? So we also have a typical testing flow battery that is commercial, just there in the floor. If we wanted to scale up some of the testing, we are not there yet. We haven't done too much with that device, but that's where we are right now. So what I'm showing you here is super cool because this is automated characterization of the compounds that were starting to be synthesized by Andres and now by Zhang. This molecular class is highly tunable. You can see their potentials from -0.1 to -0.7. So it's kind of nice, spanning a lot of water window. And again, these compounds, this is the data collected with equipment I showed you. Okay, so this is now high throughput type data in the sense that even though these were made by hand, we already have made about 180 of them, okay, with very simple systems. And here they are. Here are the 180 compounds. And our champion molecule, which you can see now on the right as this thing is having problems, has E0 of -0.5 volts. So it's kind of like a very good molecule in terms of its reversibility and in terms of its redox potential. So we believe that champion molecule is the first one that we're going to try to scale up with collaborators and then see if it's a good flow battery. Okay, but that's the number of molecules we're able to do, about 180 so far experimentally. So now let's talk about how to make this inexpensive. And I really like the fact that Ariel, in the other room as well, was telling you about inexpensive sensor systems for pesticides. Well, in this particular case, I'm going to be telling you about inexpensive electrochemical systems. We want to replace that biologics redox system because the system is actually quite expensive. It's like tens of thousands of dollars. And if I want to have many channels to actually screen many molecules, that really quickly is going to become my cost bottleneck. So then what we did is actually building the PCB of a device with the engineering colleagues, Angel Garcia at the University of Toronto, okay? And we worked with them to actually develop the system called Pocket Power Up, like, again, Mario Brothers. This is called Power Up. It's our own electrochemical system. It's about the size of a coin. So it really looks like a Raspberry Pi, but it's actually our own system. Of course, we're not the first ones to do this. Professor Aaron Wheeler, also in Toronto, has developed his own type of system, but we decided to make our own for several reasons. Aaron Wheeler created microfluidic ones, where you actually flow it and have electrochemistry in a very small microfluidic setting, whereas ours is a little bit different. But you can see here a dog or a patito or so on, with kind of the quality that our $40 device can do, right? But again, if you want to screen molecules, this might be very well enough to do your electrochemistry. Or for teaching, for example, here in the university, you could imagine giving one of these to each student, and then each one of them has a potentiostat, right? So there's a lot of reasons why you want to democratize automation in chemistry, okay? This is a good opportunity for machine learning, I would like to say. How can you change the scan speeds, think about it as a control problem? What happens if I am moving changing the potential and the scan rate as an open design problem? You could imagine having some sort of closed loop control to actually optimize parameters for screening molecules, and also to try to correlate these weird pulse sequences with properties such as stability and so on. So we're going to try to do some sort of machine learning now that we have these very, very cheap electrochemical systems. We can actually do tons of experiments, and then we can actually learn more quickly. So now, miniaturization, right? So this is the first generation of our setup. It's the 3-electrode setup I've been telling you about. What sucks about it is that if you want to leave it overnight, it can only do 20 experiments because it will use 1 liter of solvent. So you guys know how expensive solvent has become, etc. So we want to kind of make sure that we use less solvent. We're going to miniaturize so we can parallelize. So this is generation 1, and we can start screening with it, and we are. So it works. But obviously my lab is thinking about miniaturization, for example, using our flow H cells. That's the company Redox.me. And again, a little bit of 3D printed parts that you can see on the right-hand side. So we can print those parts very cheaply in a 3D printer. So when we put everything together, then each cell costs about less than $10. Right? So now you have very inexpensive $40 electrochemical controls, you have very inexpensive cells, and you can imagine parallelizing this. So, and finally, we found these screening devices that have working and counter electrodes in a little bit of chip, okay? They use 50 microliters of solution. This is a commercially available thing. Uses way less compound, 100 times less solvent. But of course, the electrodes, it doesn't matter. You don't wash them, just throw them away. Next electrode, next electrode. The problem is, how do you feed the electrochemical device? How do you kind of like go in and out and like put in the device, right? So for that, we're using the best robotics. It's called on-the-graduate soft robots, okay? So it's actually an undergraduate student, alumno de licenciatura, putting in and putting out the chip, right? So we use them as robots right now, I guess. That's probably the best thing we can do until we figure out how to automate that. But I think somewhere in between the second and the third generation, we'll find our high throughput system. But it gives you an idea of where we are. This is, by the way, only the second time I give this talk. I have not tried to talk about this because I haven't patented my molecules, but I gave it at an electrochemical meeting recently, and I said, I'm going to talk about this at UNAM because we're talking about energy. The symposium is about energy. So I'm showing you data that I have only spoken about, two times. So 150 millielectron volts of error in ionic molecules. I told you that we had about 100 millivolts error in predicting with a computer, with DFT, the redox potential of a quinone. Obviously, when you have a charged molecule, you have to think about how the solvent interacts with it. So you have to think about adding solvent models or adding explicit water molecules to the cluster. You need to think about the hydrogen bonding to the water, and work that I did with my previous student, Adrian Hinich and Benjamin Sanchez, both Mexicans. We were studying, predicting the redox potential of metabolites. So we learned how to do this. It's very expensive. You need to put a cap of explicit waters, do molecular dynamics to relax it, use an external solvent. And if you do all of that, then you might be able to lower those errors. But that's the work for Chertian to do, probably, right? Yeah, because he's our computational guru in my lab. Obviously, the biggest problem for automating electrochemistry is cleaning the electrodes, okay? And if you wanted to automate the drop sense chips, come to my talk tomorrow and I'll show you an example of how we will do it. We just used our robots to actually prepare alcoholic drinks. So we know how to move things around and etc. So in principle, we might be able to have a little robotic arm that replaces the undergraduate. Okay. And then this is kind of my last perspective slide. What we're trying to do now is to create some sort of, I don't like to use the word Manhattan Project, but it gives you the idea of what we want to do. Some sort of focused effort. These are now modernly called focused research organization around the flow batteries, right? We want to have a database with chemistry AI. We want to have synthesis, purification, and testing extremely inexpensive robots, like the one that I sent to Andres here in Mexico. And then have scale-up systems too. So I want to buy also chemical engineering scale-up reactors. That's the next step that we're doing in Toronto. We're going to buy scale-up reactors, as we went to see them at Pharma. They're about this size, and they have now liters and 2 or 3 liters or whatever it is the size for scaling. So chemical engineers like Lalo know them very well. So now we need to automate chemical engineering as well, because we need to think about how to scale up our production, right? And that will be important, right? And with that, I just gonna again thank, this is a long story why they are thanked again, only these 4, but also Yang, Han, Felix, Shertian, Marta, Andres, Marta, Carlos, Simus, and the rest of my research group. And now I'm open, no, before I do that, how much time do I have left? Probably 5 minutes or so, right? I don't know. More? Okay, 20 minutes, it's okay. We can have a lot of questions and answers. Let me tell you something about the University of Toronto, right? So maybe you probably guys don't know about Toronto enough, but Toronto is, if you think about Mexico City, then I think it's New York and Los Angeles. I forget the ranking. And then I think that's the ranking. And then the next city is Toronto. Okay? So Toronto is one of the largest cities in North America. Number 4. It's the city with the largest number of international people. Half of the people in Toronto, in the world, half of the people in Toronto have not been born in Toronto. Think about that. 200 nationalities. So if you're in the subway in Toronto, you will find people talking Russian next to somebody talking to, I don't know, some other language from any other continent that you can imagine. Okay? So that's the reason why it's very attractive for me to move there. The university has a little bit of a similarity to UNAM. It's the largest public flagship university in Canada. All universities in Canada are public. So that basically means we really want to recruit students from all over the world to these 60,000 students. For you guys, it's very small. But for us, 60,000 students is the size of our university. We are ranked quite well, depending on the rankings. Of course, we like the best ranking is the NTU ranking, that for some metrics puts us at 4th. We really like that. But there is a plot that I don't have here that I really like, that talks about the size of the number of your students and the quality of your program. Okay, and we are at a very, very sweet spot there, because some of the schools that are ranked at the top, the metrics skew to them because they have less students. They are not having an educational mission. So we also have been ranked as the second best public university in North America as well in all the rankings. So I encourage you to come to Toronto. Shertian can tell you answers about how to apply to the grad school. So when I go outside or I start answering questions from people, Shertian, stick around to me so you can also parallelize, and you can ask him about how is it to go to Toronto from Singapore, and it would be similar going to Toronto from Mexico, and give you an idea of how to come study with us. And with that, I just want to thank you. I guess I spoke faster than I thought. Thanks to Carlos and the team for inviting me. And thanks to all the previous speakers from here, from the CIFAR program, that hopefully shared some of the research with our goal of trying to remove CO2 from the atmosphere as quickly as possible. Notice I haven't talked to you anything about CO2. Even though I'm a director of the program, CIFAR is a multidisciplinary team, and therefore I'm learning about CO2 from others. So that's unique also. That's a model to think about in Mexico. How can we make teams where people are not afraid of stepping out of their comfort zone and talking to people outside of the discipline, because that's where innovation will happen. And with that, thank you very much, and I will open for questions. And I apologize for the flashing. Hopefully it was not too annoying. Thank you. Okay, I'm going to answer questions. Okay, Fraser. Fraser, by the way, is one of our advisors to our CIFAR program, Professor Fraser Armstrong from Oxford. Yes.
So I wanted to ask about how AI would analyze a complex voltammogram, because you know, in many aspects of electrochemistry, voltammograms are not just simply diffusion controlled, and they can have very bizarre shapes. You know, I mean, I've produced some of the most bizarre shaped voltammograms of all. So how would AI cope with analysing you know, I could draw something, but you know, how would you cope with analysing it?
Fraser, absolutely. So
you had a very funny one there.
It was just an example of a random one. I could imagine the funny one with a battery that has like a
one
big.
That looked like something was producing an insulator.
Exactly, insulated, and it came back. Yeah. So we actually have a theory of what that's happening, but because I'm not showing you the molecular class, you know, we cannot tell you too much about it.
It's surely the job of AI to come up with the answer.
So our idea is, and this is why I'm telling you, is something that we're doing. Again, this work is unpublished. Everything I told you about is unpublished. The idea is, once we have a series of these very inexpensive potentiostats, you could imagine having an array of molecules for training, and the potentiostats doing all sorts of weird control pulses, and generating a large data set where all these weird examples of peaks will come on. And then the question is, well, do you do first unsupervised learning? What is unsupervised learning? That might be interesting. What I mean by that is clustering. So imagine that we have all of them. Can we ask the computer, cluster all the redox phenomena, say we call them the freak redox, and see what freak classes there are. And I bet you electrochemists probably have described what is the physical process behind most of the freak processes. That is called labeling. That is now supervised, right? So if we have those clusters that are basically done with unsupervised learning, we can do what is called semi-supervised learning. We can read in the literature what scientists like you that know much more electrochemistry than me do, and say, well, I mean, Fraser says that this freak thing happened because something was degrading, or something was depositing somewhere, or I don't know, something happened, right? Then I will tag it with that tag and say deposit, question mark, etc. So we will put hypotheses on each one of those different clusters, and as the robot is doing this thing and we scan the literature more and more, we might be able to actually understand what's happening. This is how computer vision systems are trained, and something like that, I imagine, could be trained. So this is proposal. So we could collaborate on that, for example, like for CIFAR. That's a thing that I'm thinking about. I haven't seen anything in the literature, unless I'm wrong. Shertian, have you seen something about this in the literature? You read more papers than me at this point. But this will be state of the art. Nobody has done it, as far as I know.
I mean, at the moment, we just formulate an idea and do a simulation and see whether it fits.
Yeah. In this case, will be more like, in machine learning, usually you go from the other side. You go from the data. Try to collect as much data as possible, cluster it, and then explore it that way. So in some senses, less top-down, but more bottom-up. For example, I'll give you an example that is biochemical. For example, for people that know about peptides. My colleague Rob Beatty is very interested in cyclic peptides as therapeutics. So I did this approach with him. He told me that organic chemists have laboriously clustered, categorized all the conformations of the cyclic peptides. Right? If like the peptide has something coming up or down, you know, you can imagine there are very small cyclic peptides, so there's a lot of strain on the ring and a lot of interactions. So what we did is we said, let's create a library of all of them, cluster them, and see what a clustering algorithm gives us. And then we have the clustering algorithm clusters, which are called 1, 3, 5, 7. They have no name. But then Rob has the list of all the literature described ones. And we were able to match them pretty well. Of course, sometimes the literature maps to something that we clustered into three subclusters, right? Which means the literature hasn't even looked at details that are missing. So it's an interesting, also unpublished study because the undergraduate left, but of where we try to do this bottom-up approach and combine with top-down, the way chemists think, which is, I think a hypothesis, test it, and then describe what happens. So it's very exciting because you have to work with a domain expert to combine the two. I hope that makes sense. But again, this is all state of the art. It's very hard to, I don't know many literature people that are doing this. Okay, question from a student. We've been trying to encourage the students to ask questions. failing a little bit at that, but students, I don't bite. You can ask me in Spanish too if you are afraid of the English. Notice my thick accent after 25 years abroad. My accent still sucks, so don't worry about your accent. You can ask me in Spanish, anything? Okay, well, if that is the case, I guess everybody's tired from the symposium. Thank you very much for coming, and hopefully we come back again as a CIFAR group and talk to you about all this work.